The Beech Aircraft Corporation has provided checklists and procedures in your operating handbook. This airmanship learning presentation is meant to support those procedures, not to replace them. Refer to your manual for all checklists and procedures. The Beech Aircraft Corporation began producing the Baron over 20 years ago as an improvement in both size and performance over the Model 95 Travel Air. That was 1961, and the aircraft was called the 55 Baron. In 1962 and 1963, this aircraft was stretched 10 inches and redesignated the A-55. The following year, the name was changed to B-55, and that has stuck to the present. Hello, my name is Jack Wellman. I'm Director of Program Development for Airmanship Incorporated. The video presentation is based on research conducted by our instructors and is systematic in design. We will discuss the Baron by closely investigating the following systems: the engine, including mixture and exhaust, lubrication, cowl flaps and baffles, props, electrical, fuel, landing gear and brakes, flaps, environmental, pneumatic vacuum, and pedostatic. Let's begin with the engine. The early Barons derived their power from Continental IO 470L 260 horsepower engines. In 1966, the Baron family began to expand with the introduction of the C-55, powered by Continental IO 520C engines rated at 285 horsepower. The C became a D model in 1968 and subsequently an E-55 in 1970, the designation it carries today. Also in 1970, Beech rolled out the first full six-seat Baron, the 58. It utilized the same engine as its older brother, the E-55. It's important to note also that Beech marketed a 56TC Baron from 1967 until 1971, but production was halted after 95 of these aircraft were built. The 56 models were the only factory Lycoming powered Barons using the 380 horsepower TIO 541. Let's take a look at the engine. Induction air, in most cases, is available from two sources. They are filtered ram air and unfiltered alternate air. Basically, air is routed through a filter and ducted to the engine carburetor, fuel control unit, or into the engine manifold system. If this air filter is impacted with snow, ice, or any other kind of debris, a door downstream of the filter will automatically open and alternate air will then be available. When operating a normally aspirated engine in conditions that could clog the air filter, the pilot will note a drop in manifold pressure before the alternate air door opens. After the door opens, you will not have a complete manifold recovery. However, you can regain the manifold pressure by advancing the throttles. In a turbocharged engine, below the critical altitude, the pilot will not see a change in manifold pressure. The variable absolute pressure controller will automatically maintain the pre-selected manifold pressure setting. Above the critical altitude, you will see the same symptoms as the normally aspirated engine. The C-55 and D-55 Barons have a three-position induction air selector.
Unfiltered ram air can be selected to provide a slight improvement in performance. Usually this position should be selected only at cruise altitudes when the possibility of engine contamination is virtually non-existent. It is highly recommended to refrain from using this unfiltered air whenever possible. In most cases, it is the greatest source of engine and oil contamination. Now let's take a look at mixture control and the leaning procedures. From the pilot's point of view, the control of the air-fuel ratio is probably the most important contributing factor to long engine life. Improper use of the mixture control can drastically shorten engine life and cause costly repairs. For this reason, we will turn our discussion to what is considered to be the ideal mixture and the problems associated with the misuse of control. As we plot a continuous range of fuel to air ratios, at some point we will produce a mixture which develops the maximum amount of heat during the combustion process, or peak cylinder head temperature. This ratio is approximately 15 pounds of air per pound of fuel, or about 6 2/3%. As we lean the mixture past the peak cylinder head temperature, excess air will act as a cooling medium and the temperature will begin to drop. As we enrich the mixture above the 6 2/3%, excess fuel will act as a cooling medium and the cylinder head temperature will again begin to drop. So there is only one ideal mixture at which we can produce the maximum amount of heat or cylinder head temperature, this being the chemically perfect air-to-fuel ratio of 15:1, or approximately 6 2/3% fuel. Best power is obtained at a slightly richer mixture than 15:1. Best power results when airspeed is maximized per pound of fuel burned. This is accomplished by allowing some of the fuel to go unburned and provide a slightly denser mixture in the cylinder. These unburned fuel droplets also carry off a lot of heat. Most engines do not require leaning below 5,000 feet MSL. In all cases, the pilot should follow the procedures outlined in the pilot's operating handbook. Excessive leaning can lead to high temperatures, detonation, and pre-ignition, or you could actually starve the engine of fuel by operating it too lean. With an excessively rich mixture, you would have problems with high fuel consumption, ignition fouling, or loss of power and engine roughness. In a normal burning sequence, the ignition of the air-fuel mixture in the cylinder is a burning of the fuel, or what the chemists refer to as flame propagation. It is not an instantaneous explosion. In an instantaneous explosion, the entire energy which is stored within the cylinder is released in an extremely short period of time. This is what is referred to as detonation. This closely approximates an explosion within the cylinder as opposed to normal flame propagation. Instead of the piston being pushed down, it receives a hammer-like blow as the combustion forces are released virtually instantaneously within the cylinder. In its initial stages, detonation sounds are covered up by normal engine sound or prop sound. The only indication will be a slight loss of power, maybe an abnormally high cylinder head temperature, and high exhaust gas temperature. When detonation has progressed to the point of recognizable engine roughness or knock, you may be only moments away from a complete engine failure. For these reasons, it is important to avoid the conditions which will eventually lead to detonation. Most of the principal causes of detonation are either directly or indirectly controllable by you, the pilot. Mixture must be monitored carefully at all times, because the mixture will enrichen as you climb and lean as you descend, unless you make the appropriate adjustments in the normally aspirated bearings. Another major problem area which needs to be discussed is that of pre-ignition, the uncontrolled firing of the mixture before the normal spark ignition point. Pre-ignition can lead to excessive pressures within the engine. Some of the principal causes of pre-ignition are glowing spark plug electrodes, valve faces or edges heated to incandescence, or possibly a carbon or lead particle glowing within the cylinder. One final note regarding mixture. During a typical flight, after climbing to cruise altitude and leveling off, you should delay fine-tuning the mixture for 4 to 5 minutes. This allows the engine to adjust to the higher airspeed and the cooler airflow associated with the cruise portion of the flight. So allow engine temperature to stabilize somewhat in the cruise environment prior to making the final mixture adjustment. Leaning is best accomplished with extremely slow retardation of the mixture control. Rate of movement with this mixture lever should be so slow that if you were to stop, the EGT needle would stop almost instantaneously. Follow the engine manufacturer's recommendations to obtain the proper EGT for the corresponding phase of flight. Always cross-check the fuel flow indicator to confirm the proper setting. But remember, the EGT is the primary instrument. This instrument will respond to the rapid changes during the leaning process and is calibrated for the accurate readings we are looking for. The fuel flow gauge can be used to lean the mixture, but it is not as accurate as the EGT indicator. The exhaust gas temperature, EGT system, has a probe installed in the exhaust stack that comes into direct contact with the hot exhaust gases. The temperature response to the EGT gauge is quite rapid and will indicate the movement of the mixture control if it is not moved too fast. The leaning process should be done in cruise configuration with power settings of 75% or less. Let's move now from leaning to lubrication and servicing. The engine oil system is jet pressure wet sump type with an integrated full flow oil filter. Each sump has a capacity of 12 quarts. However, 13 are installed when the oil and the filter are changed because of the filter requirements. The dipsticks are calibrated for either right or left engine and are not interchangeable because of the canted position of the engines on the wing. The oil level is established between 10 and 11 quarts for normal operations and no less than 12 quarts for the longer flights. The level should not be allowed to fall below 9 quarts at any time. Aside from being a lubricant, oil has another important function. It removes excess heat fast enough for the internal parts of the engine to maintain a safe operating temperature. If the oil level is allowed to fall too low, this cooling process begins to deteriorate and the internal hot spots may then start operating at a higher than normal temperature. The hot areas of the normally aspirated engine and the turbochargers and the superchargers The Beech Aircraft Corporation has provided checklists and procedures in your operating handbook. This airmanship learning presentation is meant to support those procedures, not to replace them. Refer to your manual for all checklists and procedures. The Beech Aircraft Corporation began producing the Baron over 20 years ago as an improvement in both size and performance over the Model 95 Travel Air. That was 1961, and the aircraft was called the 55 Baron. In 1962 and 1963, this aircraft was stretched 10 inches and redesignated the A-55. The following year, the name was changed to B-55, and that has stuck to the present. Hello, my name is Jack Wellman. I'm Director of Program Development for Airmanship Incorporated. This airmanship video presentation is based on research conducted by our instructors and is systematic in design. we will discuss the Baron by closely investigating the following systems.
The engine, including mixture and exhaust, lubrication, cowl flaps and baffles, props, electrical, fuel, landing gear and brakes, flaps, environmental, pneumatic vacuum, and pedostatic. Let's begin with the engine. The early Barons derived their power from Continental IO 470L 260 horsepower engines. In 1966, the Baron family began to expand the introduction of the C55 by Continental IO 520C engines rated at 285 horsepower. The C became a D model in 1968 and subsequently an E55 in 1970, the designation it carries today. Also in 1970, Beech rolled out the first full six-seat Baron, the 58. It utilized the same engine as its older brother, the E55. It's important to note also that Beech marketed a 56TC Baron from 1967 until 1971, but production was halted after 95 of these aircraft were built. The 56 models were the only factory Lycoming-powered Barons using the 380 horsepower TIO 541. Let's take a look at the engine. Induction air, in most cases, is available from two sources. They are filtered ram air and unfiltered alternate air. Basically, the ram air is routed through a filter and ducted to the engine carburetor, fuel control unit, or into the engine manifold system. If this air filter is impacted with snow, ice, or any other kind of debris, a door downstream of the filter will automatically open and alternate air will then be available. When operating a normally aspirated engine in conditions that could clog the air filter, the pilot will note a drop in manifold pressure before the alternate air door opens. After the door opens, you will not have a complete manifold recovery. However, you can regain the manifold pressure by advancing the throttles. In a turbocharged engine, below the critical altitude, the pilot will not see a change in manifold pressure. The variable absolute pressure controller will automatically maintain the pre-selected manifold pressure setting. Above the critical altitude, you will see the same symptoms as the aspirated engine. The C55 and D55 Barons have a three-position induction air selector. Unfiltered ram air can be selected to provide a slight improvement in performance. Usually this position should be selected only at cruise altitudes when the possibility of engine contamination is virtually non-existent. It is highly recommended to refrain from using this unfiltered air whenever possible. In most cases, it is the greatest source of engine and oil contamination. Now let's take a look at mixture control and the leaning procedures. From the pilot's point of view, the control of the air-fuel ratio is probably the most important contributing factor to long engine life. Improper use of the mixture control can drastically shorten engine life and cause costly repairs. For this reason, we will turn our discussion to what is considered to be the ideal mixture and the problems associated with the misuse of the mixture control. As we plot a continuous range of fuel to air ratios, at some point we will produce a mixture which develops the maximum amount of heat during the combustion process, or peak cylinder head temperature. This ratio is approximately 15 pounds of air per pound of fuel, or about 6 2/3%. As we lean the mixture past the peak cylinder head temperature, excess air will act as a cooling medium and the temperature will begin to drop. As we enrich the mixture above the 6 2/3%, excess fuel will act as a cooling medium and the cylinder head temperature will again begin to drop. So there is only one ideal mixture at which we can produce the maximum amount of heat or cylinder temperature, this being the chemically perfect air-fuel ratio of 15:1, or approximately 6 2/3% fuel. Best power is obtained at a slightly richer mixture than 15:1.
Best power results when airspeed is maximized per pound of fuel burned. This is accomplished by allowing some of the fuel to go unburned and provide a slightly denser mixture in the cylinder. These unburned fuel droplets also carry off a lot of heat. Most engines do not require leaning below 5,000 feet MSL. In all cases, the pilot should follow the procedures outlined in the pilot's operating handbook.
Excessive leaning can lead to high temperatures, detonation, and pre-ignition, or you could actually starve the engine of fuel by operating it too lean. With an excessively rich mixture, you would have problems with high fuel consumption, ignition fouling, or loss of power and engine roughness. In a normal burning sequence, the ignition of the air-fuel mixture in the cylinder is actually a burning of the fuel, or what the chemists refer to as flame propagation. It is not an instantaneous explosion. In an instantaneous explosion, the entire energy which is stored within the cylinder is released in an extremely short period of time. This is what is referred to as detonation. This closely approximates an explosion within the cylinder as opposed to normal flame propagation. Instead of the piston being pushed down, it receives a hammer-like blow as the combustion forces are released virtually instantaneously within the cylinder.
In its initial stages, detonation sounds are covered up by normal engine sound or prop sound. The only indication will be a slight loss of maybe an abnormally high cylinder head temperature and high exhaust gas temperature. When detonation has progressed to the point of recognizable engine roughness or knock, you may be only moments away from a complete engine failure. For these reasons, it is important to avoid the conditions which will eventually lead to detonation. Most of the principal causes of detonation are either directly or indirectly controllable by you, the pilot. Mixture must be monitored carefully at all times, because the mixture will enrichen as you climb and lean as you descend, unless you make the appropriate adjustments in the normally aspirated bearings. Another major problem area which needs to be discussed is that of pre-ignition, the uncontrolled firing of the mixture before the normal spark ignition point. Pre-ignition can lead to excessive pressures within the engine.
Some of the principal causes of pre-ignition are glowing spark plug electrodes, valve faces or edges which have been heated to incandescence, or possibly a carbon or lead particle glowing within the cylinder.
One final note regarding mixture. During a typical flight, after climbing to cruise altitude and leveling off, you should delay fine-tuning the mixture for 4 to 5 minutes. This allows the engine to adjust to the higher airspeed and the cooler airflow associated with the cruise portion of the flight. So allow engine temperature to stabilize somewhat in the cruise environment prior to making the final mixture adjustment. Leaning is best accomplished with extremely slow retardation of the mixture control. Rate of movement with this mixture lever should be so slow that if you were to stop, the EGT needle would stop almost instantaneously. Follow the engine manufacturer's recommendations to obtain the proper EGT for the corresponding phase of flight. Always cross-check the fuel flow indicator to confirm the proper setting. But remember, the EGT is the primary instrument. This instrument will respond to the rapid changes during the leaning process and is calibrated for the accurate readings we are looking for. The fuel flow gauge can be used to lean the mixture, but it is not as accurate as the EGT indicator.
The exhaust gas temperature, EGT system, has a probe installed in the exhaust stack that comes into direct contact with the hot exhaust gases. The temperature response to the EGT gauge is quite rapid and will indicate the movement of the mixture control if it is not moved too fast. The leaning process should be done in cruise configuration with power settings of 75% or less.
Let's move now from leaning to lubrication and servicing. The engine oil system is generally the full pressure wet sump type with an integrated full flow oil filter.
Each sump has a capacity of 12 quarts. However, 13 are installed when the oil and the filter are changed because of the filter requirements. The dipsticks are calibrated for either right or left engine and are not interchangeable because of the canted position of the engines on the wing.
The oil level is established between 10 and 11 quarts for normal operations and no less than 12 quarts for the longer flights. The level should not be allowed to fall below 9 quarts at any time. Aside from being a lubricant, oil has another important function. It removes excess heat fast enough for the internal parts of the engine to maintain a safe operating temperature. If the oil level is allowed to fall too low, this cooling process begins to deteriorate and the internal hot spots may then start operating at normal temperature.
The hot areas of the normally aspirated engine and the turbochargers in the supercharged engines create high temperatures on the oil which subject the oil to coking and oxidation. Coking tends to dirty up the oil with carbon particles, while oxidation causes the oil to break down and thicken. A full-flow oil filter will remove most of the carbon particles produced by coking, but nothing can be done about oxidation. Both of these have a destructive effect on the oil, and if you insist on running beyond the recommended time between changes, you are just begging for trouble.
For normal engine operation, it is recommended the oil and oil filter be changed every 50 hours. In adverse climate conditions, it is safer and more economical to install fresh, clean oil at shorter intervals. Clean oil is essential to long engine life. The manufacturers recommend the use of ashless dispersant oils. However, for new or overhauled engines, in order to promote the faster ring seating that's necessary and good oil control, a straight mineral oil should be used for the first 50 hours or until the oil consumption has stabilized. Anytime a new or overhauled cylinder is installed, you should go back to a straight mineral oil and use it until the rings have seated, which is approximately, once again, 50 hours. During the break-in process, you will have a higher than normal oil consumption. So on those long cross-country flights, you may find that you'll have difficulty getting the brand of oil that you started with. There is no problem mixing brands as long as you stay with straight mineral oil. Do not add ashless dispersant, AD oils, during this break-in process. If you are using AD oil after the break-in period and run up against the same problem, there's no reason why you shouldn't mix brands of oil. The different brands will mix accurately. However, the engine manufacturers continue to recommend that you pick a brand and stay with it. There are situations when an AD oil may not be available on your cross-country travels. In this case, a straight mineral oil could be added to bring your oil level up to a safe operating level. The time period to the next oil change will not be long enough to permit a buildup of sludge and sediment deposits. At this point, we should review the procedures used in breaking in a new engine or any time you have the cylinders installed. This includes overhauled engines or cylinders. Use a good grade straight mineral oil and stay with it for the full break-in period. Change oil and filter as recommended in the pilot's operating manual. More frequent changes may be required if you are operating under dirty conditions. Every takeoff should be made at full power, and this power should be maintained until you have reached a safe maneuvering altitude of 400 feet or more. Reduce power to the recommended climb power and climb to a cruising altitude that will allow you to maintain 75% power, never less than 65%. This power is necessary for the breaking in or mating of the piston rings to the cylinder walls. The power should be maintained for these cruise operations during the break-in period. On those extended cross-country trips, every 30 minutes or so, advance to full power for about 30 seconds and then return to your cruise settings. This will help speed the break-in process. On descents and approaches, always carry enough power to keep the cylinder head temperatures in the green. All takeoffs should be made with full power and mixture in the full rich position. Leaning should not be attempted below 5,000 feet. After 5,000 feet, lean only to recover the power lost
due to the over-rich condition. In hot weather, be sure to monitor your CHT in your climbs. Climb a little shallower with higher speeds to maintain adequate cooling.
A brief explanation, I think, is in order at this point. Higher power settings are needed to develop the cylinder pressures necessary to push the rings onto the cylinder walls. The pressure has to be great enough to rupture the oil film and permit the ring to come in contact with the wall. This ring and cylinder wall contact has to be maintained until a smooth, compatible surface exists between the two. When this happens, the break-in period should be complete. It takes approximately 50 hours to complete this process if the above steps are followed. The break-in process should be completed in as short a time as possible. The only way to do this is with higher power settings. The lower power will not provide enough cylinder pressure to push the ring hard against the cylinder wall, and the break-in period would then be extended over a longer period of time. In the meantime, oxidation of the oil will begin to glaze and fill in grooves in the cylinder. If this glazing takes place before the complete mating of the ring to the cylinder wall, the result will be higher oil consumption. The only remedy in this case would be to hone the cylinders and install new rings. This could be very costly, but with the high cost of oil today, oil consumption is just a waste of money. All right, let's go to cowl flaps and winter baffles. A few words are appropriate about the use of engine cowl flaps. Too many times, pilots start up an engine, close the cowl flaps in an attempt to get the cylinder head temperature up in a hurry, especially cold weather. This practice should be avoided. Cowl flaps should remain open for start, taxi, takeoff, and climb operations. To do otherwise will produce distorted cooling and hot spots in the cylinders. The unequal expansion or contraction of the cylinders imposes undue wear on the moving parts in the cylinder. Eventually, the damage over a period of time shows up as broken piston rings, scored pistons or cylinders, and possibly an early overhaul. Extremely cold operations, cowl flaps can be adjusted to maintain cylinder head temperatures in the normal operating range after cruise climb has been established. The higher air speeds in the climb will provide the ram air pressure needed within the cowling to force the air around the cylinders the way that it was intended to be. The cowl flaps can be completely closed in the climb just prior to leveling off and building up the normal cruise speed. The cowl flaps will close easier before the ram air pressure builds up. Some aircraft use a small electric motor to actuate the cowl flaps. Closing the cowl flaps prior to leveling off will reduce the load on the actuating motor and extend the time between overhaul or replacement periods. The cowl flaps should remain closed for cruise operations. In all cases, the cylinder head temperature should be maintained within the operating limits as published in the pilot's operating handbook. During descent and approach, cowl flaps should remain closed to prevent rapid cooling. If there is a go-around, there will be ample time to open the cowl flaps to maintain cylinder head temperatures within limits. It is more important to prevent the rapid contraction of the metal parts that is associated with this shock cooling. This will eventually cause cracks in the cylinders, the spark plug holes, or any openings that are subject to stress and fatigue. Once the aircraft has landed and is turned off the runway, the cowl flaps can be opened before taxiing to the parking area. The non-turbocharged engines normally can be shut down without special procedures after you've parked. A turbocharged engine requires a cool-down period after landing to permit the turbocharger to slow down and cool off before shutting down the engine. In all cases, follow the procedures outlined in the operator's handbook. Winter baffles are used on many aircraft to help maintain normal operating temperatures in cold weather operations. Special kits are available on many models. However, a note of caution should be injected at this point. The use of winter baffles in high ambient temperature conditions could make it difficult to maintain engine temperatures within the operating limitations. In most cases, the baffles should not be used when ambient temperatures are 70 degrees Fahrenheit or higher. Once again, consult the pilot's operating handbook for information about this. Associated with the higher operating temperatures will be a higher oil consumption, especially when you have light oil in the sump. If a cross-country trip takes you to a warmer environment and you plan to do some flying under these higher temperatures, it would be advisable to remove the baffles. Continued operation with the baffles under these conditions would result in extremely high oil consumption. As much as a quart or more per hour could be consumed. Now let's turn our attention to the propeller system. We use the term system because there are several components: the blades, the pitch change mechanism, the prop governor, and the cockpit controls. Now that we have broken the system down, let's discuss each component in detail. Blades deserve close observation during pre-flight for nicks, stress cracks, or abrasion. Any type of damage exceeding 1/8 of an inch in depth should be referred to a certified mechanic for repair. Do not attempt to perform minor maintenance on the prop unless you hold the proper license. Remember, these blades must carry a centrifugal load at full RPM of nearly 25 tons. Also, anytime the surface of a prop is abraded in any way, the corrosion protection is lost, and that prop should be retreated. Many Baron and other light twin owners unknowingly subject the blades and the hub to unnatural stresses on a regular basis. The pre-flight feathering check should be done at relatively low RPM, and then only allow the prop to spin down a maximum of 500 RPM. The prop check, done at the higher RPM, is a governor check only. And during the check, the prop levers should never come aft to the feather detent. To do so creates unnaturally high stress on the prop and the hub. The pitch change mechanism includes all the hardware in the dome of the propeller. Several forces are at work in this area, the sole purpose of which is to physically regulate propeller blade angle. All the Baron prop systems utilize boosted engine oil pressure to move the blade to the high RPM or low pitch position. Now, a gear-type pump in the base of the governor steps up the engine oil pressure to approximately 275 pounds per square inch operation. Oil pressure is the only force moving the blades towards low pitch. Depending on the blade and hub combination installed on your Baron, there may be as many as 3 opposing forces constantly tending to drive the blades toward the high pitch or low RPM, ultimately to feather. These opposing forces are air charge, springs, and counterweights. Consult your prop owner's manual to learn exactly which of these items are installed in your system. The prop blade shanks are connected through linkages to a piston which slides fore and aft within a cylinder in the hub. On one side of the piston is an oil chamber, and on the other side is an air chamber with a specific air charge. As high pressure oil is introduced, the air pressure, spring, and counterweight pressure, if installed, are overcome and the blades move toward low pitch. As oil pressure is released, the opposite occurs, and the blades move to high pitch. The question now arises as to why the prop doesn't continue right on down to feather when the oil pressure is removed, such as during an engine shutdown. In fact, this would happen if it weren't for some locking pins or latches, which extend when centrifugal forces decrease during the spin down of the prop. These latches mechanically engage stops on the blade shanks, which restrict the blade from moving to a higher blade angle. This action generally occurs around 800 RPM. From your point of view, this is a very important consideration because any loss of engine in flight will require feathering. If the engine is allowed to spin down too far before the levers are pulled into feather, the latches will engage and make feathering impossible unless you can speed blades up somehow. Now let's turn our attention to the brains of the prop system, the governor.
It determines whether oil pressure will be directed to the pitch change mechanism or be allowed to dump from it. This regulation of the direction of oil pressure is accomplished by two dynamic opposing forces within the governor itself. The first of these forces is a spring tension set by you as you reposition the prop levers in the cockpit. This speeder spring is opposed by forces generated by spinning flyweights. The flyweights will spin at a speed directly related to engine speed because they are attached to a shaft which is geared to the engine. If the flyweights are spinning at a speed fast enough to overcome the speeder spring tension, the pilot valve will be forced up, allowing oil to return from the prop pitch change mechanism and dump back into the engine case. This is what we call the overspeed condition of the prop governor.
In other words, the prop is turning at a faster speed than what you have selected with the prop lever.
As the oil dumps from the prop, the blade will go to a higher pitch, slowing the engine and reestablishing an on-speed equilibrium condition.
On the other side of the coin is the underspeed condition. In other words, the prop is turning slower than what we have selected with the prop lever. In this condition, the speeder spring tension overcomes the flyweight resistance, forcing the pilot valve down. Oil pressure is now directed out to the prop pitch change mechanism, causing the blades to move to lower pitch, allowing the engine to speed up. In reality, all these actions occur almost instantaneously. Automatic adjustments we have just discussed are constantly occurring. The governor has one additional function, which we must address now, and that is feathering. When the prop levers are pulled into feather, the pilot valve is mechanically lifted up, allowing all oil to be forced from the prop, and the latches are held out of the way, allowing the blades to go to full feather. Now, some bearings also incorporate unfeathering accumulators, so let's take a brief look at them. Accumulators are either the ball type or the cylinder type, both utilizing the same principle of operation. The ball accumulator has an air chamber and an oil chamber separated by a flexible diaphragm. The cylinder accumulator uses a piston to separate the same two chambers. The air or nitrogen precharge in each of these types is usually set around 100 pounds per square inch. The oil side of the accumulator is plumbed into the governor and will be at the governor boosted pressure of approximately 275 pounds per square inch under normal conditions. When the prop levers are pulled to feather, a check valve traps the oil in the accumulator, and the rest of the oil from the prop dumps back through the governor to the engine case. When the prop levers are again moved full forward
To accomplish unfeathering, this trap pressure is released through the governor to the prop, and the blades move toward low pitch.
When this happens, ram airflow on the blades will crank the engine. It's important that these accumulators be checked at regular intervals to ensure proper precharge. This completes the discussion of the bearing and prop system. The electrical circuit in the aircraft is the single ground return type. This means is that it takes only one wire to power the components that are placed from one end of the aircraft to the other. All are grounded to the airframe. This type of system gives us a tremendous savings in weight and materials, and the system design lends itself to simpler maintenance and simpler service procedures. The primary components of the electrical system are the batteries, alternators, voltage regulators and overvoltage relays, and the load meters.
The batteries are used for normal starting, absorbing system surges or spikes, and for emergency electrical power in the event a double alternator failure should occur. Most battery installations have two 12-volt lead-acid batteries connected in series to give us a 24-volt system. There are advantages to having two 12-volt batteries instead of a single 24-volt unit. For one thing, they are easier to handle and easier to service.
Some places just do not have the equipment to service 24 volts. On a 12-volt battery, even a service station can help you in a pinch. As a matter of economics, it's a lot cheaper to replace a 12-volt battery than a 24-volt unit.
The battery is located beneath the floor of the nose baggage compartment. The battery box is vented overboard to dispose of the electrolyte and hydrogen gas fumes that are discharged during normal operation. To be sure these fumes are disposed of properly, it's a good idea to frequently check the vent hose connections at the battery box for obstructions. The electrolyte level in the battery should be checked every 25 hours of operation. The level should be maintained by adding distilled water only. Add only enough water to cover the plates and never more than 1/4 inch over the separator tops. Normal operations may not require much service. However, hot weather operations may dictate more frequent checks. The battery check is seldom done by most owners or operators, but it is a very inexpensive way to head off costly repairs and possible replacement due to a low, dead, or frozen battery. Remember that a low battery can freeze with temperatures as high as plus 13 degrees Fahrenheit, whereas a fully charged battery will still be reliable at nearly 80 degrees below zero. The battery is connected to a battery bus by a heavy wire. The battery master switch controls the power from the battery to this bus by a solenoid-controlled contact. If this solenoid fails, there is no way to power the battery bus. A more common failure is the diode that guards the solenoid. Anytime you activate the battery switch and nothing happens, the diode would be a good suspect if the battery is fully charged. An external power unit may be used for starting should the batteries be too low for good cranking power. The battery master switch should be on and the alternator switches placed off. This procedure protects the voltage regulators and the system electrical equipment from power surges. The batteries are now being charged by the external power unit. The batteries act as a shock absorber should the external power unit malfunction and send a voltage spike into the aircraft. Whenever you elect to make an external power start, open the pilot's operating handbook and follow it verbatim. The second major component in the electrical system is the alternators. They vary in output from 50 to 100 amps for different aircraft models. Each alternator is supplying power directly to the battery bus. The bus is now supplied by power from 3 sources: the battery and 2 alternators. In normal operations, the alternators will supply the system needs and will also charge the battery and keep it fully charged automatically. If the alternators fail, the fully charged batteries will have approximately 30 minutes of reserve power for normal IFR operations. When forced to operate on battery power only, due consideration must be given to preparation for landing. Depending on conditions, 30 minutes of operation on battery power may be an optimistic assessment of the amount of electrical power which remains. Some of the things that need to be taken into consideration include the power requirements of the gear motor, the flap motor, landing lights if necessary, and the gear indication lights. Each alternator is capable of supplying the power needs for a normal daylight operation. However, night operations may require more than the output from one alternator. This will depend on the equipment requirements of your particular operation. Each alternator output is indicated by its respective load meter. They give a percentage reading of the load on the system. The percentage reading may be converted into a load amperage. For example, a 25% reading means the alternator is putting out 25% of its capacity. If it is a 50 amp alternator, that means it is putting out 12.5 amps. In other words, 0.25 times 50 equals 12.5. The alternators are controlled by 2 transistorized voltage regulators, but only one regulator is operable in the system at any one time. The second is used as a standby regulator. When switched into the circuit, either regulator will adjust the alternator outputs to the required electrical, including battery recharging. The voltage regulator also has a paralleling circuit that divides the load between the 2 alternators.
If the load differential becomes too great, the regulators should be switched to see the problem still exists. If it does, a problem may be developing on one alternator or in the circuitry involved. At any rate, this is the time the system should be checked out. It's not a good idea to let one alternator carry the full load. An undervoltage or overvoltage alternator condition would illuminate the respective alternator out lights. Undervoltage could be caused by alternator failure or voltage regulator malfunction. Corrective action would be to switch to the standby regulator. If the light remains on, the alternator should be switched off. An overvoltage trip would occur if the alternator output exceeds 32 volts. Again, switching to the standby regulator may solve the problem, or turning the alternator off and back on, which will reset the overvoltage relay. In any emergency, if it is necessary to operate on only one alternator, you should reduce the system load so that you are not operating at 100% capacity. It is better to maintain an output that will not peg the load meter. Continual operation above 100% will cause an overheat and eventual alternator failure. If you operate below 100%, you can monitor actual load outputs and you will be assured of operating within the load limits of the alternator. If a load meter breaks down or becomes inoperative, this should not affect the output of the alternator. This is very easily checked by the reading on the good load meter. If one load meter is normal and the other reads 0, the output of the alternator associated with the 0 load meter can be found by turning that alternator switch off. If the good load meter indication does not increase, then it was carrying the entire load all along and you have a failed alternator. If the load increases substantially when the suspected alternator is turned off, then the alternator was good and you simply have a bad load meter.
The avionics master switch, generally located in the upper left-hand portion of the pilot's panel, allows the pilot to operate all the items on the avionics bus with the use of one switch. However, protections must be provided in case that switch should fail. As we know, all electrical switches will fail from time to time. This failure would be indicated by a simultaneous loss of all the avionics equipment. In this case, the manufacturer has provided a system that will direct power to the avionics bus through the avionics master circuit breaker. Now, this is generally located in the right-hand sub-panel. This circuit breaker controls a solenoid which provides a backup source of power for the radio equipment.
With the avionics master switch in the on position and no power to the entire avionics package, all that is necessary is to pull out the circuit breaker for the avionics master switch. All of the affected equipment regains power. This can be demonstrated on the ground by leaving the avionics switch off and, after engine start, turning on the battery and alternator switches and then pulling the circuit breaker for the avionics switch. In the event of an electrical fire in the aircraft, it is necessary to remove all the power from the electrical system. This can be done quickly simply by turning the battery and alternator switches off. Once this has been accomplished, you can turn off the rest of the individual electrical components. Impending electrical fire may be indicated by an excessive load meter indication. One option is to shut down the entire electrical system as just described. Then, with the battery and the alternator switches back on, you can rebuild the electrical system by individually turning on essential equipment while noting the load meter indication. The faulty equipment may be detected and isolated. The faulty equipment can be detected by an excessively high draw on the load meters when that component is turned on. Turn it off. Pull the appropriate circuit breaker and leave the component without power until it's inspected and repaired. Ensure the fire is out. Turn off the cabin heat switch and push in the cabin air control. The pilot's storm window may be opened if required. Battery problems are not easily detected in a system without a battery charge rate monitor. Unless you constantly monitor the load meters, you cannot detect an impending problem. This is what an ammeter does. It shows only the charge or discharge rate to the battery. This is one reason you would make a battery check to determine the charge rate, especially if you suspect a problem. In a load meter system, the battery charge rate can be checked by the following procedures. 1. If in flight, shut down one alternator and note the percentage load indicated on the one load meter. 2. Turn off the battery master switch and notice the difference on the load meter. If the battery is fully charged, there will be very little change. An abnormally high rate of charge on the battery would be indicative of a faulty voltage regulator. Remember, the function of the voltage regulator is to control alternator output supplying the electrical system load, while at the same time keeping the battery at a full state of charge. With a faulty voltage regulator, you could be overcharging the battery, causing the battery to overheat, and in severe cases, possibly create a battery fire or explosion. If you find that the battery is constantly in need of fluid replacement during your periodic battery checks, this could be an indication of a faulty voltage regulator overcharging and overheating the battery. 3. A normal battery will require only a trickle charge to maintain its full charge condition. During an engine start, there will be a large drain on the battery. When the alternators are put on the line, there will be a high charge rate that will gradually diminish until the battery is fully charged. This usually takes 5 to 10 minutes to complete this charge cycle. If the battery condition was low to start with, it could take a little longer period to recharge back to normal. 4. A fully discharged battery should not be in the aircraft during an APU start. This battery could accept a high rate of charge over a longer period of time, and this could overheat the battery. This could boil out the water, or it could buckle the lead plates and eventually damage the battery beyond repair. It would be better to remove batteries and have a bench charger hooked up. This way the batteries can be charged at a lower rate and the battery condition monitored during the recovery period. 5. A battery that has a dead cell or shorted plates will continue to demand a charge. This can be detected on the load meter if there is indeed a short. The battery check will continue to show a higher charge rate as long as the battery is in the system. The battery can be isolated by turning off the battery master switch. The flight could still be continued to your destination with the alternators continuing to supply the aircraft's power requirements. Let's turn now to the fuel system. The fuel system is a simple on-off cross-feed arrangement. The selector panel contains a fuel selector for each engine and a schematic diagram of fuel flow. The Barron fuel system comes with 3 tank options: the 142, 172, and 200-gallon capacities. The unusable fuel on all 3 systems is 3 gallons per side. Some older Barron models have an auxiliary tank position, and this system also incorporates a lockout device for crossfeed, which means you cannot select crossfeed on both valves at the same time. Fuel crossfeed is used only during single-engine emergency operations and in level flight only. The systems cannot be used to transfer fuel from one wing system to the other. As in any emergency situation, be sure to follow your checklist. A vapor return line returns excess fuel from the engine to its respective wing system. Fuel quantity is measured by a float-type transmitter unit which transmits the common level indication to a single indicator for each respective wing. The fuel from the integrated cells passes through another strainer and then to an auxiliary pump located in the gear well.
The fuel flows to the engine-driven pump, then on to the fuel distributor. The excess fuel from the engine-driven pump is returned through a one-way check valve to the tank in use. The fuel system also incorporates a vent line check valve and a pressure relief valve to equalize tank pressure by allowing fuel to exit or air to enter the tank system. Once the pressure is equalized, a siphon brake stops the continued siphoning of fuel. When the wet wingtip fuel system is installed, each fuel quantity will read full until the fuel level reaches approximately 75 gallons. Then, as the remaining fuel is used, each indicator will move and indicate empty when all the usable fuel is consumed. When installed, a visual fuel level sight gauge in each wing leading edge, outboard of the engine nacelle, can be used for partial filling or offloading of fuel. This gauge is to be used only when it reads within the calibrated area. A minimum of 13 gallons of fuel is required in each main or wing system before takeoff. If you are not sure that you have at least 13 gallons in each main or wing, it would be wise to add fuel so that you are sure that you will have a minimum in each wing. You should plan for a good reserve for any flight that you make. For example, a minimum of 13 gallons of fuel is required for takeoff in each wing or main tank, depending on your model. This is also a good rule of thumb to observe for landing fuel reserve, because it will provide 1 hour of flight time if properly managed. Over and above this minimum, each situation will dictate additional fuel levels based on alternate and other contingent requirements. Some of the newer Barons have an extended range fuel system with an additional wingtip tank. Be sure to open this cap first to verify full fuel. Opening the inboard cap with full tanks will cause an overflow situation and a possible fire hazard. It's your responsibility to determine that the fuel quantity indicators are functioning and maintaining a reasonable degree of accuracy so that they can be used to facilitate your flight planning and fuel loading. This check can be made at the time when you fill each wing system by correlating the fuel pumped with the readings on the fuel gauge. The Model 55 and 58 Barons utilize a 2-speed electric auxiliary fuel pump for each engine. High pressure is used for providing fuel pressure for priming before engine start, and it will provide near maximum engine performance if the engine-driven fuel pump fails. The high pressure position should not be used while the engine is operating except in the event of the engine-driven fuel pump failing. The high pressure mode supplies a greater pressure than can be accepted by the injection system during normal operation. The low pressure can be used in any operating mode to eliminate fluctuations due to high ambient temperatures and or high altitude operations. Let's now turn our attention to the landing gear system of the aircraft. Landing gear is operated by push-pull tubes connected to a gearbox located between the pilot and co-pilot seat under the spar cover. This box and actuator assembly is driven by an electric motor or a hand crank. Another device incorporated in the landing gear system is the dynamic braking relay. Notice the position of this mechanism with respect to the landing gear motor and the main actuators beneath the pilot seat. The dynamic braking relay incorporates sensor switches which gently brake the landing gear into position when lowered. As the landing gear nears its down and lock position during the lowering cycle, these switches send a signal to the dynamic braking relay. This relay, in turn, switches the gear motor from a motor function to a generator. This then will stop the action of the gear as it reaches the full down and lock position. Failure of the dynamic braking relay or its associated sensing switches would be indicated by unusual shaking of the aircraft as the landing gear reaches the full down and lock position. This situation should be corrected because over time
it will have a detrimental effect on the landing gear components.
In the main gear, separate actuators are incorporated for the gear struts and the inboard gear doors. When the landing gear is lowered, the inboard main gear doors open, followed by the lowering of the main gear and finally the closing of the inboard main gear doors. The nose gear doors are mechanically linked to the nose gear strut mechanism. Therefore, only one actuator is necessary for raising or lowering the nose gear. Gear indication lights consist of a red transit light and 3 green lights. The red indicates the gear that it is not fully up nor fully down and locked. The green lights indicate a down and locked position for each landing gear.
Early model Barons had a red light indicating up and a single green light indicating down, plus a mechanical nose gear indicator. If you don't receive a positive down and locked indication on all 3 gear, it may be advisable to recycle. If this does not correct the situation, follow the gear emergency procedures and mechanically crank the gear against its stop. This should put the gear into its locked position. This can be verified by checking that all 3 green lights are illuminated. Micro switches can fail as any mechanical unit can, but manually cranking the gear hard against the stops will assure you of the gear being in the full stop or locked position.
There are speed limitations to be observed in the extension or operation of the gear. The main reason is the possible damage that can be inflicted on the gear doors. The gear itself can withstand the air loads, but the gear doors could possibly be warped or damaged.
This could pose a problem if you were to retract the gear with damaged doors. Jamming the gear could be a definite possibility. If the gear doors were subjected to these loads for whatever reason and you suspected possible damage, it would be wise to leave the gear in the down position until they could be checked by a competent mechanic. If the landing gear is extended for emergency reasons, do not move any landing gear controls or reset any switches or circuit breakers. It is possible the malfunction is such that it could cause the gear to retract. Nothing should be touched until the aircraft is put on jacks where a gear check can be made.
In order to reduce the possibility of raising the landing gear while the aircraft is on the ground, the manufacturer has incorporated a safety switch located on the main gear strut, which deactivates the landing gear motor circuit when the aircraft is on the ground and the main gear strut is compressed. The pilot's operating handbook does warn, however, that the switch should not be trusted. While the aircraft is rolling at 20 to 40 knots, the wings are still developing some lift. Should the aircraft hit a bump on the runway, the main gear struts will extend, and the aircraft will sense an in-flight condition. If at the same time the pilot is contemplating raising the flaps and mistakenly grabs the landing gear switch, the landing gear will retract. This accounts for a major percentage of gear-up accidents. Quite possibly the most important aspect which can be stressed is that there is really no need to accomplish any checklist while the aircraft is still rolling out on the runway. It is far better to turn the aircraft off the runway, come to a full stop, communicate with the controlling agency, and run an after-landing checklist at that point under controlled conditions. In the event the landing gear cannot be electrically operated, the gear can be manually extended but not retracted. The procedure would be to 1. Slow the aircraft. This greatly reduces the physical effort involved in lowering the gear to the full down and locked position. 2. The gear selector is then placed in the position. 3. Pull the gear motor circuit breaker. 4. Remove the manual crank cover and engage the crank. 5. Turn the crank counterclockwise 20 to 30 turns, pausing to add a few inches of manifold pressure to to compensate for the drag increase caused by the gear moving into the airstream. Resume cranking until the gear reaches the stop and the 3 green lights are illuminated. Total travel takes approximately 51 turns. And 6, after the gear is down and locked, disengage the crank and stow it, replacing the cover plate. This will ensure that you have manually disengaged the crank from the drive gear, because the cover plate will only fit if you have folded the handle back properly. The landing gear warning horn is intermittent. Many pilots have confused this with the steady stall horn. If there is any confusion in the critical phase of landing and you are not sure of the gear position, it would be best to apply power and go around. The landing gear horn should be set according to manufacturer's recommendations. An inoperative gear horn, or one that is set too low, defeats the purpose of the safety feature. If it is set too high, the horn would be blaring at you unnecessarily. This could add to the confusion under certain circumstances. The horn should not be sounding off during normal approach power settings. It should only sound off if either or both throttles are retarded below a power setting that will not sustain 2-engine flight with the gear up. The setting on this aircraft should be set at approximately 12 inches of manifold pressure. Anytime the gear is activated, do not try to reverse the process. The gear has completed its cycle. To do so would put undue stress on the motor and the gearbox components. The motor is turning at a very high RPM, and to reduce it immediately creates arcing on the commutator and excessive wear on the motor in general. Let us examine the possibility of a partial gear indication after extension. We will assume that you have attempted to lower the gear by manual extension and perhaps have placed various G-loads on the aircraft in attempting to free the landing gear, which may not have reached the full down and locked position. There are no definite rules to be observed when confronted with partial gear landing. Each situation will be different depending upon weather conditions, wind, type of runway surface, or pilot proficiency. All these things have to be taken into consideration in preparing for a partial gear landing. Consider these alternatives. In the case of an unreliable nose gear indication, you would like to land with the 2 main gears extended, holding the nose off as long as possible until we run out of elevator control. Then gently lower the nose to the runway or other smooth surface and allow the aircraft to come to a complete stop. If, however, 1 main gear and the nose gear are extended, the situation may lend itself more appropriately to a complete gear-up landing. It would be very demanding on pilot technique to attempt to land with 1 main gear extended and the nose gear extended, attempting to hold the wing with the faulty gear indication off the ground as airspeed gradually decreased. Therefore, we recommend in this situation, to minimize damage possibilities or personal injury, simply to land with the gear retracted. If a gear up land is necessary, the following procedure is recommended. 1. Select a landing site of firm sod or a foamed runway. 2. Close the cowl flaps. 3. Select the desired wing flap position. 4. When assured the aircraft will glide to the touchdown point, close the throttles. 5. Position the fuel selector to off. 6. Position the mixture controls to idle cutoff. 7. Turn the battery, alternator, and magneto switches to off. 8. Keep the wings level during touchdown. 9. Exit the aircraft as soon as it stops. It is necessary to discuss the possibility of experiencing a flat strut. Obviously, if the aircraft has a flat strut while on the ground, no attempt should be made to taxi or tow the aircraft. If the strut should go flat while in flight, you would not realize this condition until landing.
In this case, we strongly recommend that the aircraft be maneuvered only to exit the main flow of traffic on the active runway. Get a maintenance facility to service the strut temporarily. At that point, the aircraft can be moved to the maintenance facility to undergo permanent repairs. Again, it is important that the aircraft not be moved with a flat strut. Just moving the aircraft a short distance in this condition can result in excessive abrasion and scoring of metal parts. If this happens, the condition won't be corrected merely by servicing the strut or replacing a seal. Permanent damage is incurred at this point, which can only be corrected by replacing the entire strut mechanism. Let's turn now to brakes. Our discussion of landing gear is not complete without a few notes on the brake system. First, let's briefly review how the system functions. Brake fluid is stored in a small reservoir in the nose baggage area. This reservoir should be checked for a full indication at regular intervals to ensure proper brake operation and no air bubbles bleeding into the system. If the reservoir needs servicing, be sure to fill it with the correct type of fluid. In most cases, MIL 5606 hydraulic fluid, sometimes called red oil. This is a mineral-based fluid, and virtually all bearings use this specification. Other types of fluid are available, such as Skydraw, which is usually purple in color. Extreme care must be exercised to ensure the correct type of fluid is used, because Skydraw and other ester-based synthetic fluids will damage the seals and contaminate the entire brake system. This will necessitate flushing the system and replacing all the seals. When you apply the brakes, you direct this brake fluid under pressure to a pair of pistons on each main wheel. As the pistons move out, they force the brake pads or linings to contact and create friction against the brake disc, which is part of the wheel. On some installations, there may be an additional backplate with a second lining, creating a squeezing action and more effective braking. Brake linings are generally made of an organic material with particles of brass or copper embedded to provide proper friction coefficients. Pure carbon pads are also becoming popular because of their lightweight and heat dissipation characteristics. The linings should be checked on every pre-flight to ensure wear limits have not been exceeded and no damage or uneven wear characteristics are noted. It's a good idea to consult your bearing maintenance manual for the maximum allowable brake wear limitations. This limitation may be measured in different ways. Now, on some installations, you will look at the interval between brake housing and disc with the brakes applied. On other installations, you will just look at the lining thickness itself. Be sure you know how to determine when the wear limits are becoming critical. Most bear and brake systems will be either Goodyear or Cleveland. Both systems are very reliable, with the major difference being that the Cleveland disc bolts to the wheel assembly instead of being an integral part of it. This makes disc replacement easier and less expensive. Abnormalities or malfunctions in the brake systems take many forms. Let's discuss a few of the more common ones. Spongy pedal, usually an indication of air in the system, and it will have to be bled off. Solid pedal, but poor braking. Linings virtually gone, must be replaced. Also check discs for scoring. Brakes won't maintain pressure. That's a possible leak. Parking brake won't hold. That means air in the system or bad parking brake valve. Squealing or chattering brakes. This condition is harmful to both the landing gear and the brake structure, usually caused by warped or glazed disc. Glazing can occur when excessive braking has been used, and the intense heat generated can cause lining material to adhere to the disc. This will cause uneven friction when the brakes are causing the chatter or squeal. This condition should be corrected. As a final comment, use brakes as little as necessary, and only after dissipating some speed after landing, and you will greatly increase both brake and tire life. If you ever need to jump on the binders in an emergency situation, don't hesitate to use them. But then, have them inspected for heat and stress damage. Brake housings can lose their strength and even crack when overheated, and the seals will have to be replaced. Keep these concerns in the back of your head if you ever have to push those brakes to the limit. Let's go to the flap system. The flaps are operated by an electric motor-driven gearbox located above the landing gear box. The gearbox has 2 cable drives, and each flap has its own drive and jack screw. Notice the location of the flap motor mounted in the aircraft directly above the gear motor. You can see the cable drives leading to the flap actuators in the wings. The limit switches in the left wing serve to stop the flaps in selected positions. In the older aircraft models, there are only 2 limit switches, one for full up and one for full down. In the newer aircraft models, which incorporate an approach flap position, there are 3 limit switches. The flap limit switches are located on the inboard end of the left wing in the recess between the wing trailing edge and the flap leading edge. Flap limit speeds published for the various models of this aircraft vary slightly throughout the years, but it should be emphasized that if only one flap limiting speed is published for your aircraft, that speed applies for any flap position, whether it is an approach position or a full flap position. The newer aircraft models have an advanced flap system in which there are 2 limiting speeds, one published for a higher speed, and that being the approach flap setting, and one for a lower speed for anything beyond the approach flap setting. The susceptibility of the flap limit switches to moisture contamination must be emphasized, especially while in the flap down configuration. On a wet or slushy runway, it is not recommended to take off with a partial flap setting due to the possibility of impingement of ice, slush, or water in the limit switch area. As the aircraft climbs, this moisture accumulation could freeze and render the flap limit switches inoperative. Also, after landing, the switches may become covered with freezing slush and cause the motor to continue to run while placing the switch back in the up position. Under these conditions, the motor could drive the flaps against the stops and not have the protection of the cutoff switch. A few motors have been burned or damaged before the circuit breaker popped. Another possibility is washing the aircraft in a warm hangar in the winter and splashing water in the limit switch area. When the aircraft is moved out onto a cold ramp, the freezing of these limit switches can occur. Remember, during the pre-flight, it is important to examine these switches and to check the flap security. In order to do so, it is necessary to lower the flaps to the full down position. Place your hand on the flaps to note any play which may occur. You should also look inside the flap wells to see if possible obstructions exist. Also examine the limit switch area. Remember that the only structural attachment of the flaps to the wing, the actuating rod, and the flap guides. The flap operation should be given the same consideration as the gear operation. Do not reverse flap operation until a cycle is completed. There are situations where this may be necessary, however, but I want to stress that continued reversal will not do the motor or any of the associated components any good. Should the electric motor or actuator fail, or perhaps a cable jam, we are committed to using whatever flap position was previously selected. If one of the drive couplings should break or become disconnected, you will have an asymmetrical flap condition. For this reason, we prefer to extend the flaps in level flight, especially when close to the ground. Asymmetrical flaps in a turn could surprise you, especially if you have a flap extending on the outside of the turn and the inside flap is stationary. This should not pose a problem to you if it happens in level flight. If this does happen, a good flap can still be controlled and retracted as necessary to match the inoperative flap. There are benefits to having partial flaps in your approach configuration. This will give you a level flight attitude, and you will also have a zero reference on the artificial horizon. The zero reference on the instrument will make your IFR work a lot easier with less fussing and less adjusting of your instruments. If you are flying in icing conditions, this level attitude will expose the smallest frontal surface area to ice exposure. The ice you do collect will in most cases collect on the frontal areas of the wing and aircraft. We will consider at this time a few good reasons why full flaps will be used in the final approach phase. The greater lift results in a speed and permits a lower touchdown speed. The greater drag permits a steeper approach angle without increasing speed. The slower touchdown speed and the extra drag of full flaps result in a shorter landing roll. This slower touchdown and the resulting slower ground roll will cause less wear and tear on the brakes, tires, and landing gear components. Also, the slower approach speed would give you more control on the ground if a swerve should occur. One aircraft manufacturer stated in the owner's handbook, quote, that it is generally good practice to contact the ground at minimum possible safe speed consistent with existing conditions, unquote. We would like to emphasize, however, that you should be familiar with the landing characteristics under approach flaps or no flap conditions and should practice these options at frequent intervals.
Under a no flap condition, remember, final approach speed should be increased 10%, and in so doing, the ground roll will increase by 20%.
If you are landing in a high wind condition, you really shouldn't be that concerned about the need for full flaps. The high winds will take care of the actual touchdown speeds. Under these conditions, partial or no flaps may be in order to make the aircraft more stable and less susceptible to gusts. In a no flap condition, always add 10% to your normal final approach speed to preserve the interval above the stall. It's also a good technique to add the full gust increment to your target final approach speed for safety. Let's now move to the environmental system.
A combustion heater in the nose cone supplies heated air to the cabin by outlets located forward of the pilot and co-pilot seat, the rear of the co-pilot seat, and the rear of the right passenger seat. A fifth outlet provides heated air for windshield defrosting. In flight, fresh ram air enters an intake on each side of the nose cone, passes through the heater, and is distributed to the cabin outlets as fresh outside air. This same air can be heated and is ducted through to the same outlets. Heat regulation is obtained by pulling the cabin air control, which regulates an iris valve restricting the amount of incoming air to be heated. To obtain maximum heat in the cabin, pull the cabin air control partially out to reduce the volume of incoming cold air and permit the heater to raise the temperature of this air. Pushing the control knob in will bring in a large volume of air that is warm but not hot. Be careful not to pull the control more than halfway. To do so will activate a micro switch that will render the heater inoperative. The volume of air available for the various outlets can be controlled by adjusting the controls individually to obtain the desired results. When the three-position switch on the pilot's subpanel is placed in either the heater position or the blower will operate if the landing gear is in the extended position and the cabin air control is more than halfway in. The blower will automatically shut off if the landing gear is retracted or the cabin air control is pulled out approximately halfway. During ground operation or during slow flight with the gear down, a blower will supply the ram air necessary for heater operation. If dangerously high temperatures should occur during the heating operation, a heat-actuated circuit breaker located will shut the heater down. However, the blower will continue to operate and cool down the heater in plenum. If this malfunction should occur and cause the circuit breaker to pop, the heater should be checked before attempting to operate it again. For ventilation during ground operation, push the
cabin air control full forward and place the heater switch in the blower position.
In flight, fresh ram air from the intake on the left side of the dorsal fairing is ducted to the individual outlets above each seat. A master control on the overhead panel, just aft of the front air outlets, enables you to adjust the amount of ram air available to all outlets above each seat. This overhead flow, combined with the airflow through the heater plenum, provides a more than adequate volume of fresh air to cope with extremely high temperatures during flight.
Some caution should be mentioned at this time in regards to heater operation.
1. Be sure to cool down the heater and plenum prior to shutting down. Shutting down a hot unit will cause uneven contractions that could eventually damage some of the heater components. 2. A good procedure is to shut off the heater as part of your after-landing checklist. This allows the heater and components to be gradually cooled by the ram air flowing through the heater. 3. If the weather is extremely cold, the cooling process could be delayed until the final few minutes of taxi time. At this time, you can select the blower position to cool the heater prior to engine shutdown. If the blower runs but the heater will not start, the over-temp circuit breaker could have tripped. The ignition unit may have faulted, the igniter fouled, or the fuel filter may be clogged. If the heat produced is inadequate, if the thermostat is not properly adjusted, the fuel filter is plugged, or perhaps there are restrictions in the fuel lines, be sure to have an authorized mechanic troubleshoot any problems. Okay, let's go to the pressure system, pneumatic vacuum de-ice. Until 1976, all Barons utilized a vacuum concept to drive instrumentation. Since that time, the aircraft have used pressure pumps to supply the instruments and vacuum pressure for de-ice boot hold down from the opposite side of the pressure pump. The pressure system is operated by air intake through the ambient air filters located forward of the rear engine baffle on each engine. This filtered air is then passed through the two engine-driven dry air pumps to the pressure regulators located on the top side of each nacelle behind the firewall. These regulators reduce the pressure of the air from the pumps to a preset level, then passes it on through a pair of inline system filters to a pressure manifold. This manifold is located aft of the front spar behind the upholstery panel in the left-hand sidewall. Air is then taken from the manifold forward through an adjustable orifice or a regulator valve, depending on the model, to the instrument panel. Air is plumbed off the manifold to operate the de-ice boots and the autopilot if installed. The de-ice system incorporates a distributor valve which functions to direct pressure or vacuum to the boots as selected by the pilot. This valve is spring-loaded to the vacuum or hold-down position and requires electrical power to move to the pressure position. So if the de-ice boots fail to deflate, the circuit breaker may be pulled if power is locked on to the distributor valve. All right, time now for the pitot-static system. A standard pitot tube for your flight instruments is installed immediately to the left of the nose gear doors. There is an option for a pitot tube to the right of the nose gear doors for the co-pilot's instruments if installed. The pitot system needs no drain because of the location of the components. The static system receives its static air from two ports, one located on each side of the aft fuselage. These ports are tied to a single line in the aft fuselage and then run forward to the rate of climb indicator, the altimeter, and to the airspeed indicator. The static air line is drained at the emergency static air source position. A word of caution: do not attempt to clear static or pitot lines by blowing into them or using air pressure of any sort. The instruments involved can immediately be rendered useless. This airmanship video presentation has covered the Baron systems of engine, including mixture and exhaust, lubrication,
cowl flaps and baffles, props, electrical, fuel, landing gear and brakes, flaps, environmental, pneumatic and vacuum, and pitot and static. We hope this presentation increases your safety, confidence, and flying pleasure while reducing pilot error, equipment malfunction, and expense. This program has not touched on every aspect of flying the Baron. We have not discussed a vast list of topics important to the proficient Baron pilot. We haven't touched on emergency procedures, cockpit standardization, departure en route approach procedures, VN diagrams, weight and balance, turbulence penetration, or performance. Some of these are covered in other airmanship videos.
Hello, my name is Jack Wellman, and I'm Director of Program Development for Airmanship Incorporated, the knowledge center for today's pilots. You will note that our title states that these tapes are designed for the non-professional, professional pilot. Although that may sound somewhat redundant, we don't intend for it to be that way, and let me explain. One concept most of us have about the word professional is an occupation for which a person receives compensation. We speak of professional truck drivers or professional actors or professional educators as people with training and experience in their chosen career field. Another concept of the term professional, which has developed over the years, is that of the person who really knows what he or she is doing, regardless of whether or not it falls within that person's chosen line of work. Have you heard someone say, take your TV to Bob Davis? He's a real pro when it comes to repairing television sets. Or how about the neighbor who's been audited by the IRS 4 times and has come out clean each time? Now that's a real professional, even though the guy drives a bus for the local transit line. Airline and corporate pilots, for the most part, qualify as professional pilots. They not only earn their living at flying an airplane, but they study airplanes and how the airplanes fly. The company they work for usually requires them to go to school periodically, a school like airmanship. Most of them know everything about the plane they fly, and they have a thorough knowledge of how most airplanes fly. Many of the pilots who ask airmanship for training are not professional pilots. The airline pilot has his training taken care of by the company, but the people who come to airmanship want to be professional pilots, as in the second definition of the word we presented. Many of our students earn their living doing something other than flying airplanes, but they would like to be a real pro when it comes time to fly their own planes. So this course is designed for many of you, the pilot who has a career but who wants to know his own aircraft better and wants to have the professional pilot's knowledge of how airplanes fly. The topic of aerodynamics is a technical one, filled with jargon, formulas, and graphs. Although I can't completely separate myself completely from all of that, I will limit as much of the highly technical stuff as I can, and will stick to the basic concepts. In this first tape, I will revisit with you some of the areas you studied when you were first learning to fly. We will discuss the atmosphere, its composition, and its properties of pressure, density, and viscosity. Next, we will examine the 4 forces which act upon an aircraft in flight. We will look at an airfoil, name its parts, and establish terminology important to understanding the generation of lift, such as angle of attack, camber, angle of incidence, and chord line. The principles and laws and Bernoulli will be explored along with the theory of circulation. As a result of this, the relationships among camber, relative wind, and angle of attack should be well established in your mind. Except for scientists who study it or environmentalists concerned about its quality, most people give little thought to the air which surrounds them. But if you're counting on it supporting you immediately after rotation from the runway, you should reacquaint yourself with it. Almost everyone remembers that dry air is 78% nitrogen, 21% oxygen, and 1% other gases. The ratio of these gases remain the same around the world and as high as the atmosphere extends. Water vapor is also a gas found in the atmosphere. Its quantity may vary, unlike the other gases whose ratio is pretty well constant. It may make up from near 0% of the atmosphere to a maximum of about 5%. As the amount of water vapor increases at a given point, all other gases are reduced proportionately. When water vapor is absorbed by the atmosphere, it reduces the molecular weight of the air. It makes the air thinner, so to speak, because a molecule of water vapor is actually lighter than a molecule of air. It seldom affects aircraft operation by itself. The total amount of water vapor, even at saturation, is too small for that. However, in a takeoff requiring maximum performance, the amount of humidity in the air may be an overlooked ingredient which could take years off a healthy person's life. Most of us probably know that air is a gas and as such has all the properties of gases. It has mass and weight. It can exert pressure. It can be compressed or diffused, causing changes in its density. And it can be liquid. It offers resistance to objects moving through it. All of these properties are at work when you fly your plane through the atmosphere. Let's first look at the word, or the words, static pressure. Remember the 14.7 pounds per square inch you learned in junior high school science? That was supposed to be the normal air pressure? That is static pressure. You probably remember a specific number without any qualifications. However, the figure is an arbitrary one and only pertains to sea level on a, quote, standard day, unquote. If you went to school in North Platte, Nebraska, the figure that you learned as normal air pressure was about 1.5 pounds per square inch off. Air pressure on a standard day in North Platte is more like 13.2 pounds per square inch. Static pressure, then, is the force exerted by the weight of the atmosphere pressing down from hundreds of miles in space. It is pressing down because it has mass and is reacting to the pull of gravity. If that is so, why isn't the pressure equal regardless of the altitude? Why does North Platte, at a little over 2,800 feet, have over a pound of pressure less than at sea level? One of the other properties of air helps us to explain it. Compressibility was mentioned earlier. The more weight exerted upon a gas, the more dense it becomes. A column of air 1 foot square, extending out to the limit of the atmosphere, weighs a little over a ton at sea level on a standard day. For each minute measurement upward, away from the Earth, there is less weight pressing down. This means that the atmosphere at that point is a little less dense. The higher we go from the Earth's surface, the less weight there is above us. There is less pressure of the gases in the atmosphere, and the pressure exerted becomes less. With less pressure exerted on it, the remaining air takes up an ever-increasing volume. Researchers have pretty well established that about half the atmosphere exists below 18,000 feet, while the upper half continues out for hundreds of miles into space, simply to fade away into immeasurable amounts. Before we leave static pressure, I'd like to point out that we have been discussing it on the basis of a standard day. A standard day rarely happens. It's simply a norm based on weather observations over many years. We all know that the atmosphere is in a constant state of turmoil, with huge mounds of air piling up in places, leaving other spots with a thinner layer of air above them. Therefore, our definition of static air pressure is the pressure which results from the mass of air supported above it at the altitude or elevation from which the measurement is being taken. I've made reference to density, so let's discuss that next. It is simply the amount of mass in a cubic measure. For example, air under standard sea level conditions weighs 0.0765 pounds per cubic foot. At 10,000 feet, a cubic foot of air would weigh only 0.0565 pounds. This means that close to the Earth, there is a great many more molecules in the air in a given measure than in a comparable measure at a higher altitude. Unlike solids and liquids, gases have the ability to change density by great amounts in a short period of time. In our atmosphere, these are due primarily to the varying amounts of heat which the atmosphere is subject to around the Earth. Air density varies directly with pressure and inversely with temperature. Although the density of the atmosphere is greatest at sea level due to the weight of the atmosphere, it will become less dense as it is subjected to high temperatures. The air also has a property called viscosity, as do other gases and liquids. Now, most of us have heard the term and think of oil we put in an engine when we hear the word. The numbers on the can tell us something about the oil, but not really its thickness, as is it's a common assumption. Viscosity is the tendency of an air or liquid to cling to an object and to itself. It possesses the qualities of adhesion and cohesion. It is somewhat like the wad of bubble gum you step on from time to time. It wants to stick to the ground, but it also wants to stick to your shoe at the same time. And it wants to stick to itself, and in so doing stretches out to a breaking point. Air is similar to the gum as it rushes past your aircraft or your car for that matter. Because of viscosity, there is a boundary layer of air adjacent to the wing's surface which is less than an inch thick in most cases. It affects how efficiently your plane flies. Viscosity is not the most important concept in aerodynamics, but is one you should know about. Dynamic pressure is one of the most important concepts in aerodynamics. It is air pressure created by movement of air. Aerodynamically, it represents the kinetic energy of the free airstream. It is determined by density and velocity. Dynamic pressure varies directly as the density and as the square of the velocity. In other words, if density is decreased by 1/2, the dynamic pressure would be decreased by 1/2. However, if the velocity of the airstream is doubled, the dynamic pressure would increase by 4. Let's take a look at a chart which represents a standard day, one of those we mentioned earlier. This illustration is an excerpt and not the complete chart, which was originally put together by the National Advisory Committee for Aeronautics, the predecessor to NASA. The chart is based on many years of weather observations, and since it was published, has been confirmed as basically accurate. Its purpose is to provide a common denominator for the measurement of aircraft performance and to provide a standard upon which to calibrate and correct the readings of some aircraft instruments. The chart will be important when we discuss aircraft performance and in other presentations dealing with instruments. Before dealing specifically with any one of them, let's take a moment to review the 4 forces acting on an airplane in flight. You know them as thrust, drag, lift, and weight, or gravity as some prefer to call it. The 2 forces which are constantly trying to bring you to a stop on the ground are drag and gravity. The 2 forces which you must produce to overcome these negative forces are thrust and lift. Thrust must be able to overcome drag, and lift must be able to overcome gravity before the plane can get off the ground. In a stabilized flight condition, such as level flight, climb or descent at a constant velocity, thrust and drag are equal, and lift and weight are equal. The propeller is producing a given thrust, but the total drag equals that thrust and limits the speed of the aircraft. The weight of the plane, plus a little extra aerodynamic weight, is equaled by the lift produced over the wings. In aerodynamics, this stable condition is known as equilibrium. What happens when the throttle is advanced, increasing the power? Well, the plane will accelerate until drag, once again, is equal to the total thrust, and the speed will stabilize at a new setting. The plane will climb due to an increased relative wind over the wings. Once the new rate of climb has been established, lift and weight will again be equal, and the plane will climb until the factor of air density degrades performance enough to stabilize it at a new altitude. Now that was brief, but I just wanted to reactivate the image of the 4 forces which have probably been dormant in your subconscious for quite some time. Before we leave it to go on to a deeper study of lift and drag, let's look at why some texts refer to weight and some to gravity. Now, the noted author Asimov explains weight as a force with which a body is attracted to the earth. In other words, it only acts in one direction, toward the center of the earth. Using the word weight in that sense would never allow an airplane to weigh more than 1 g. Now, if you've flown a plane for very long, you know that there are many times when your arms have felt so heavy that they could hardly leave your lap. What has happened is that other forces, such as centrifugal force, have combined with weight to make it seem as though you and your plane are heavier. The aviation community has adopted a scale to express this combination of forces. It's called G-forces, and its units are in multiples of the plane's weight. 2 G's are twice the loaded gross weight of the plane. Positive G's are always directed toward the bottom of the plane, regardless of its attitude, and G's are directed towards the top of the plane. It is these G-forces that lift must oppose, and not simply the weight of the plane. Now we come to the big question. What is lift, and how is it produced? Before we get the answer, let's look at some pictures and review some more terms. An airfoil is any part of the plane shaped so that it responds to air movement by producing differential pressure on either side of the airfoil. The wing, propeller, and empennage are the important airfoils. Leading and trailing edges of the wings seem to be pretty obvious, but they do more than just outline the silhouette of a wing. Their location has much to do with the aerodynamics of an airfoil. A line connecting the leading and trailing edges of an airfoil is referred to as the chord line. It should not be thought of as being a permanently anchored thing, since it moves as the high lift devices change the shape of the wings. Its position in relation to the relative wind and the longitudinal axis of the aircraft are extremely important. Camber means curving or bending. On an airplane, it refers to the curving surfaces. A wing which has identical curvature top and bottom is known as a symmetrical wing. An asymmetrical wing usually has a flatter lower surface with more curvature on top. Relative wind is the airstream created by the movement of the plane through the air. Most of the time, its direction is opposite the flight path of the aircraft, but it may be deflected by gustiness or wind shear. Angle of attack is the angle between the relative wind and the chord line of an airfoil. Increasing the angle of it will increase lift and also drag. It also determines the point at which a wing will stall. A given wing will always stall at the same angle of attack, regardless of speed or attitude. It is rare that a manufacturer fits a wing to an airplane so that its chord line is parallel to the longitudinal axis of the plane. In normal cruise flight, they want the fuselage to be parallel to the ground, but it must be able to support maximum gross weight at the same time. Therefore, the wing is set into the plane at what is called the angle of incidence. This provides just enough angle of attack so that the pilot should not have to trim beyond a neutral position. The generation of lift is based on the Bernoulli principle, which in turn has its basis in the law of the conservation of energy. Let's look at this diagram of a tube with a restriction at midpoint. At point A, the potential energy is represented by static pressure. When the air flowing through the tube reaches the restriction at point B, it doesn't just pile up, it speeds up. The increase in velocity at point B means that some of the potential energy has been converted to kinetic energy. The law of the conservation of energy requires that total energy in the tube remain the same. Therefore, we have taken from the potential energy to create some kinetic energy. Since we said that potential energy was represented by static pressure, we have reduced the static pressure by using some of its potential energy to create greater velocity at the restriction at point B. After the airflow passes the restriction at point B, its velocity decreases and the pressure increases. If the velocity at point A and C are the same, then the pressure would be identical. Another important concept in the generation of lift is circulation. If you are a baseball fan, you probably have seen its effect on a pitched fastball. Look at this diagram of a cylinder and an airflow. We will ignore density and viscosity at this point. Note the pattern first where the cylinder is stationary, and in the second illustration where the cylinder is rotating. The circulation of the cylinder has produced not only a larger amount of lift on its top side, but it has also produced an upwash ahead of the cylinder and has moved the stagnation points toward the bottom. There are normally two stagnation points on an airfoil. They occur along the leading and trailing edges of an object placed into an airstream. At the leading edge, where the air separates to go either above or below, a small area exists where there is no air movement. At this point, a stagnation pressure develops, which is the sum of the ambient pressure ahead of the wing and the dynamic pressure around the wing. A similar area occurs along the trailing edge of the airfoil. Apply this concept to baseball. The pitcher puts some topspin on the ball as he throws. The highest velocity exists over the top of the ball, creating lower pressure there than on the bottom. This lifts the ball. It actually bobs up from the plane in which it was thrown. And if it's a good fastball, the batter will undercut it completely. Back to airplanes. Compare the cylinder diagrams with two diagrams of a symmetrical airfoil. Note how similar the illustration of the airfoil at zero angle of attack is with the non-rotating cylinder. There are stagnation points fore and aft, and reduced pressure is equal top and bottom. Now look at the diagram where the cylinder has been placed in rotation. Lift forces on the top, where velocity is greatest, has increased, while the opposite is true on the bottom. The stagnation points have moved to a lower position. The net result is a positive force acting perpendicular and upward from the cylinder. The position of stagnation points is of additional importance to you. It is the leading edge stagnation point that has the area where ice formations start. Because of the stagnant air at this point, the ice sometimes develops almost a horn shape, which continues to build out beyond the stagnation area under some circumstances. The symmetrical airfoil, tilted to a positive angle of attack, shows very similar pressure patterns. Note also the upwash ahead of the airfoil and the downwash behind the trailing edge. The airfoil appears to have the same circulation around it as does the circulating cylinder. This helps explain why velocity of the airstream over the wing accelerates as the wing is placed in motion. It is subject to the same type of circulation. One more observation deserves our consideration. The symmetrical airfoil at small angles of attack may develop negative air pressure both top and bottom. It will be true, however, that the least pressure will still be on the top of the wing. It is also true that at high angles of attack, the pressure on the surface will be increased. It will force large quantities of air down in the downwash coming from the airflow over the top of the wing. In this situation, up to 1/3 of the lift force may come from the increase in pressure. So far, I have presented you with three important concepts on the production of lift. First, the Bernoulli principle utilizes the theory of conservation of energy, and it explains why air placed in motion over an airfoil reduces the pressure. Second, the theory of circulation helps us to understand why the velocity of air flowing over the wing is greater than that flowing beneath the wing. Third is Newton's third law, which states that there must be a reaction for every action. We know that large quantities of air are forced downward behind the trailing edge of the wing. If we force air downward, the reaction in nature is to force the wing up. Now that we know why lift is produced over the wing, let's take a look at how engineers determine the amount of force produced by this phenomena. It will involve a mathematical equation, but not one that you should find very intimidating. The formula for lift looks like this. Lift equals the coefficient of lift times 1/2 of the density times the velocity squared times the wing surface area. All of the items seem obvious except coefficient of lift. This item is an index number representing the ratio between lift pressure and dynamic pressure. It is related to the shape of the wing and the angle of attack. The maximum lift coefficient for any wing occurs at the point of the stall. We know that a wing will always stall at the same attack. We therefore reach the maximum coefficient and the stall angle of attack at the same time. This has implications for landings and takeoffs. For illustrative purposes, let's place two aircraft on a runway side by side. All factors are equal except the maximum coefficient of lift. Airplane A has a maximum coefficient of lift of 1.8 with a thick asymmetrical wing, while B has a thin symmetrical wing with a coefficient of 1.0. Which plane will use less runway for its landing and takeoff? It will be the aircraft with the highest maximum coefficient of lift, or in this case, aircraft A. Now, would it be possible to modify airplane B without changing to another airfoil and be able to equal the landing and takeoff performance of airplane A? Yes, it would. We could cut loose a section of the wing at the trailing edge and hinge it so it would kind of droop down. Why don't we call it a flap? Since shape is considered in our index, we bend the flap down until we get a camber which will be equal to 1.8 as its maximum coefficient of lift at the maximum angle of attack. Now, we can use the same landing and takeoff figures for both aircraft. Additionally, we can retract the flaps while in cruise and have the benefit of a cleaner airfoil with less drag. The lowered coefficient of lift will be compensated for by increased speed. This chart was taken from Aerodynamics for Naval Aviators. It shows that the coefficient of lift varies directly with the angle of attack. How is it possible that a diminishing angle of attack and a lower coefficient of lift can keep an aircraft in the air? The answer is your airspeed. Note on the line, which correlates index numbers and angle of attack, that selected airspeeds are also given. You will find that as the angle of attack and the coefficient of lift diminish, the airspeed increases. Many instructors use this information to demonstrate that control of airspeed is primarily a function of angle of attack. They further claim that power is used to control altitude. Although discussions on this topic have appeared in the journals from time to time, it is well accepted that attitude controls airspeed and power controls altitude. Well, we ought to regroup here for a moment. We have just determined that there are basically three things which determine how much lift you will get over your wings. They are relative wind, angle of attack, and camber. They are interrelated so that what affects one has an effect on another. For example, let's take a plane in straight and level flight. If we retarded the throttle and began to lose altitude, you would automatically adjust the angle of attack if you wish to remain in level flight. This would reduce your airspeed, but by increasing the angle of attack, you have increased the coefficient of lift, which gave you the lifting force you need to remain at a given altitude. There have been many pilots who have lost airplanes because they didn't understand this relationship. Take the full flap go-around as an example. Cleaning up flaps means reducing the coefficient of lift to that of a clean wing. Getting rid of flaps all at once without giving the plane a chance to accelerate
and compensate for this loss may mean a stall and most the loss of altitude at a crucial point. The FAA often states that the stall spin accidents are the most common type of fatal accidents. All pilots learn early in their training how to make an airplane stall. Instructors point out to them through movies and diagrams how the air burbles after the critical angle of attack has been reached. However, people still have stall accidents in disturbing numbers. It is important in any discussion of aerodynamics that we review stalls. We will start with airflow around a wing at zero angle of attack. When we do this, you must remember that we have sliced off one cross-section of the wing. Other patterns of airflow will be occurring at other places around the wing at the same time. The ideal situation would be for the airstream to flow smoothly around the camber of the wing's layers. This is referred to as laminar flow. Most wings start with laminar flow at the leading edge, but it is converted to a turbulent flow toward the trailing edge. Just aft of the forward stagnation point, a boundary layer is formed in the laminar flow. Because air has viscosity, it wants to cling to the wing surface where its velocity theoretically is zero. It also starts to hang together like the bubble gum mentioned earlier, so that it tends to hold the boundary layer to the wing. Within the boundary layer are velocities ranging from zero at the wing surface to the velocity of the dynamic air in the main layers of the airstream. The boundary layer is usually only a fraction of an inch thick. Somewhere behind the point of maximum thickness of the camber, the airstream cannot hold to its smooth boundary layer. It becomes turbulent. As long as it has a strong enough velocity, it will remain layered. Stagnation pressure from the trailing edge of the wing is quite powerful. The velocity of the turbulent layer diminishes as it nears the trailing edge, and the airflow along the wing may actually reverse direction due to the trailing edge stagnation pressure. What would cause the turbulent layer to lose velocity? When the angle of attack is increased, it becomes more difficult for the boundary layer to cling. The circulation effect produces an upwash at too great an angle over the leading edge. This allows the turbulence layer to spread toward the leading edge. Because it is turbulent, its velocity is decreased, and the trailing edge stagnation pressure amplifies the airflow separation. At the stall angle of attack, this separation is complete. All you have left to keep you in the air is the downward deflection of the air from the bottom of the wing. Unfortunately, some training manuals leave you with just the images of the wing sections and their airflow patterns. Well, a wing just doesn't behave that way most of the time. First, it is designed so that its stall pattern follows a known progression. A well-designed wing will stall first at the trailing edge near the wing root. Except for the T-tail aircraft, this places the tail surfaces in turbulent downwash, which produces the buffeting that is your warning of an impending stall. It also leaves the tips to stall last, which gives some degree of aileron control up to complete stall. It also helps prevent the plane from developing some nasty wing drops to stall, which could happen if the tips stalled first. Your wing may still be flying when the stall breaks. The reason the nose falls through the horizon with suddenness is that there is a complete stall close to the fuselage, which eliminates the downwash over the horizontal stabilizer. Your plane depends on that downforce to balance a nose-down pitch built into it at the factory. With the tail force gone, the pitch force takes over and drops the nose. By stalling the wing root area first and having the stall progress outward from the fuselage, the pilot is given a warning of an impending stall. The nose will automatically pitch downward toward recovery, and aileron control will exist well into the stall, but not after a complete stall. The way that designers get the wing root to stall first is usually to twist the wing by giving it a smaller angle of incidence at the tip than it has at the root. It is only a matter of a couple degrees, but it does the job. It is also possible that the airfoil near the tip is of a different shape than the airfoil in the main wing section. If the coefficient of lift is higher at the tips, it will mean that the tips will remain flying after the main wing has stalled. Another technique in inducing root stall first is to place a small triangular strip on the leading edge near the wing root. At high angles of attack, these strips disrupt the smooth airflow over the wing enough to induce early airflow separation and will initiate the stall at that point. A point worth repeating concerning stalls is that they can occur in any aircraft attitude and at any airspeed. A snap roll at the top of a loop when the plane is inverted is a stall maneuver. High-altitude aircraft cruising just under Mach 1 have stalled in clear air and have fallen thousands of feet before recovery. The angle of attack at which a given airplane will stall is always the same. Your stall warning device is set to trigger at a few degrees below the stall angle of attack. Remember that the next time you make a tight turn from base onto final, believing that just a little extra airspeed will compensate for the higher angle of attack needed to support the airplane. During the discussion on the forces of weight and lift, I mentioned that your aircraft will be called upon to support more than its loaded gross weight on occasion. This will occur when extra G-forces are experienced and can happen during a maneuver as simple as a turn into the pattern. At the other end of the scale would be the upgusts in, say, severe turbulence. Lift must support the total weight of the plane. This means that if your plane weighs 3,500 pounds and is in a turn pulling 1.3 Gs, the total aircraft weight which lift must support at that moment is 4,550 pounds. If you increase the angle of attack to produce the extra lift necessary, the plane will slow down. It is easy to see that angle of attack by itself cannot compensate for total weight of the aircraft under some circumstances. It will be necessary to add power in order to keep below the stall angle of attack. The high lift device you are most familiar with is the trailing edge wing flap. I discussed with you earlier how you could increase the coefficient of lift on a wing by lowering the flaps. Some aircraft have been modified so that the ailerons droop as much as 15 degrees with the flaps and still operate as ailerons. This gives the plane full span flaps, which increase takeoff and landing performance considerably. Modern aircraft are equipped with any of four types of flaps. They are the plain flap, slotted flap, split flap, and Fowler flap. Their primary purpose is to allow for steeper landing approaches by increasing the coefficients of lift and drag. Many general aviation aircraft use a version of the plain flap, which is essentially a section of the trailing edge which can droop to, say, around 40 degrees. The slotted flap is related to the plain flap. The difference is that the flap is pushed back away from the wing as it comes down. This allows high-energy air from below the wing to be ducted over the flap. The renewed airstream gives the boundary layer the velocity needed to delay airflow separation longer, which increases the coefficient of lift even more. A close look at a Cessna high-wing airplane will give you a good picture of this type of flap. The flap used on the Goonie Bird, the legendary DC-3, is called a split flap. In this type, just the lower surface of the wing droops down instead of the entire trailing edge section. Its coefficient of lift is slightly better than the plain flap, but it produces great quantities of drag. The Fowler flap not only droops to change the camber, it also uses a portion of the undersurface of the wing to increase wing area by sliding it aft as it is lowered. The total wing surface is one of the prime factors in the lift formula. A flap which can increase the coefficient of lift and at the same time increase wing area will greatly to the lifting force. that is what the Fowler flap does. However, it needs a complicated mechanism and some pretty heavy hardware, which makes it expensive to install on the average general aviation airplane. High-performance aircraft will often include lifting devices on the leading edges as well as the trailing edges. Here's why. Earlier, we discussed how the boundary layer converted to a turbulence layer slightly aft of the point of maximum wing thickness. With flaps down, the turbulence layer tends to separate from the surface more readily. The boundary layer needs a dynamic shot in the arm, and that is provided by opening a contoured slot along the leading edge of the wing, which allows the boundary layer to pick up enough momentum to delay the onset of the turbulence layer, which improves the coefficient of lift. The movable slat is the most common leading edge high lift device. It is either automatically operated by the airflow or operated manually by the pilot. In addition to allowing for a smoother airflow over the wings, these leading edge slats or flaps also change the camber of the wing and improve the coefficient of lift. It was the automatic retraction of the leading edge flap on the left wing of the DC-10 in Chicago which caused the wing to stall, rolling the aircraft out of control. Experimentation continues with devices designed to control the boundary layer for the full width of the wing. The engineers have been quite successful with boundary layer control, but have yet to figure how to eliminate the miles of plumbing necessary to make it work. The two major systems either bleed air from the surface through hundreds of tiny holes to a suction pump, or force air through the holes from the compressor section of the cabin engine. Either way provides the aircraft with a new, higher stalling angle of attack. Although results have been good, the cost-benefit ratios have not yet been positive enough to put it into production models. We have now scratched the surface of aerodynamics by helping you understand perhaps a little better the concept we call lift. We know it is a direct product of properties and conditions which prevail in the atmosphere. Static and dynamic pressure, density and viscosity of the air around us determine conditions for the production of lift. We have dissected a cross-section of the wing and named its parts: leading and trailing edges and chord line. We have defined and differentiated between angle of incidence and angle of attack. We discovered how a wing produces lift by examining the theories of Bernoulli, dealing with the conservation of energy, of Newton, dealing with action and reaction, and the theory of circulation, explaining increased velocity over the wing. We discussed relative wind, camber, and angle of attack. Stalls were revisited and expanded upon. Finally, we discussed high lift devices and how they affected the production of lift. Generating lift over the wing of an airplane would be simple if we could stop right here. However, we have already gotten involved with drag on several occasions, and drag deserves some time of its own. So right now we will terminate our present discussion. To continue with us in this airmanship series of tapes on aerodynamics, you should go next to the tape entitled The Development of Drag. Welcome back to Airmanship series of lessons on aerodynamics. My name is Jack Wellman, and in this session I will take up the subject of the development of drag. Before I go any further, I would like to remind you that this tape is the second in a series. Aerodynamics is developmental, so you should have worked with me on the generation of lift, our first presentation in this series, as a prerequisite. If you have not worked on Lesson 1, the generation of lift, remove this cassette from your VCR and replace it with number 1. Before I plunge into the elements which determine drag on an aircraft, let's look briefly at what we did in our first presentation. We'll be dealing with all the properties of the atmosphere which affect the generation of lift. Let's take 30 seconds to write down a list of them.
Your list should resemble this one. Atmosphere has mass and weight, exerts pressure, can be compressed or diffused, can flow like a liquid, and offers resistance to objects. Now pause for another 30-second break and create a new list. This time list all the terms we used in connection with the generation of lift. Most of the terms you will have on your list would be as follows: airfoil, chord line, relative wind, angle of attack, angle of incidence. Our discussion of lift was based on three well-accepted scientific laws or principles: the Bernoulli principle, Newton's third law, and the principle of circulation as it pertains to a rotating cylinder in a free-moving airstream. We will refer to these again in this presentation. Lift equals the coefficient of lift times dynamic pressure times wing surface area. That is the equation used to calculate total lift produced by a wing. Keep in mind that the coefficient of lift is a dimensionless ratio between the lift pressure and the dynamic pressure. Think of it as a measurement of how efficiently a particular airflow generates lift at various angles of attack. In this presentation, we will be dealing with the drag coefficient, which I will have more to say about later. The other two topics I dealt with in tape 1 were stalls and high lift devices. I have divided aerodynamics into several topics for the sake of study. Be aware that everything I describe in these tapes is going on all the time and at the same time. The atmosphere becomes a very busy place once you place an airfoil in motion through it. Now, we all know drag opposes thrust. It goes to work as soon as the air starts to move the airframe. It's always with us as we fly, and we even make good use of it at times. As pilots, we can't do anything about most of it, but we do have some control over one type. Most of us learned that there are two types of drag. They are parasite drag and induced drag. You buy parasite drag with the airplane. Its design and general condition will determine how much there will be. Induced drag is a product of lift, and this is where you can exert the most control. I will take a parasite drag with you first, and we will see what we can do to keep it to a minimum. It has several subdivisions, which we will look at one at a time. They are form, skin friction, interference, separation, pressure field, power plant, and wing section profile. Form or flat plate drag is sometimes referred to as the barn door effect. It is created by the total frontal area of the plane and includes not only the fuselage, but gear, struts, wires, and antenna as well. Many ultralights have large quantities of form drag, part of which is the human body hanging below the wings. Skin friction drag is created by the rubbing of the air molecules against the total exposed surface of the plane. It is directly proportional to the amount of surface and the roughness of the surface. Many home-built planes made of composite materials can be rubbed to a super smooth finish, thereby eliminating a good chunk of skin friction drag. There is a tendency for the airflow to break down and separate wherever an appendage meets the fuselage. This creates what the engineers call interference drag. Some of this type of drag can be eliminated by placing streamlined fairing where the wings, landing gear, struts, and etc. meet the fuselage. Separation drag is interference drag in that it is the result of design problems. It may occur wherever there is an abrupt contour change in the fuselage shape. The switch from the straight razorback fuselage to bubble canopy on some of the World War II fighters, such as the Spitfire, P-47, and P-51, caused a breakdown over and around the tail surfaces, necessitating the addition of a ventral fin ahead of the regular vertical fin.
While the ventral fin did not totally compensate for drag, it did restore directional stability. Whistling doors are a clue to the fact that you may have what could be referred to as pressure field drag. It occurs around leaky doors, cowlings, and all control surfaces. You can install new door seals and tighten up cowlings, but the leakage around the control surface is a design problem that modification or redesigning may take care of. Power plant drag consists of the energy used in cooling the cylinders, providing ram air to the carburetor, and driving accessories. Cowl flaps allow for adequate cooling during ground operation and high horsepower maneuvers, but are closed in cruise to eliminate some of the power plant drag. In selecting the airfoils which will be used on a particular aircraft, the engineers must be concerned with wing section profile drag. Section profile means that the airfoil shapes taken from cross-sections of the wing at various stations are being considered. The designer must consider such things as the ratio of maximum thickness to chord. At what point along the chord will the maximum thickness occur, and what kind of curves will be used. This information is not only important in determining the coefficient of lift, but also of the section profile drag. The ideal airfoil section would have a high coefficient of lift with a low profile section drag. Since this is an impossible design to come up with, every section airfoil is a compromise. It's further compromised by other considerations such as the thickness of the main spar and whether flaps or ailerons will be part of that airfoil. In summary, wing section profile drag is extremely important to the aircraft designer in establishing the efficiency of the wing for a particular aircraft. Total drag consists of all these parasite drags plus induced drag. Your control over parasite drag consists mainly of keeping your plane clean and waxed and sealed up tight. You do have some control over induced drag, so let's talk about that. Placing a wing in motion produces both lift and induced drag. It's like having a date with Siamese twins. If you take one, you have to take the other, regardless of how ugly the other one might be. We look at lift as being the desired twin and drag the ugly one. I'm sure you've heard an unpleasant date partner described as a drag, but we know that one must look deeper than the epidermis to discover all the qualities of a person. Maybe we can apply this to induced drag as well. I'd like to go back to the circulation theory dealt with in the lift tape. The next three diagrams will illustrate how induced drag is produced. I've taken a few technical liberties with them and have incorporated some slight exaggerations, but they are basically true representations. In diagram 1, we show a hypothetical situation of level flight with a neutral angle of attack and an asymmetrical airfoil. In order to remain, lift must equal weight. The lifting force opposing weight we will call effective lift. It is blue in color. In this situation, the effective lift is equal to the total lifting force of the wing. Total lifting force is red. Before we go to diagram 2, a word about average relative wind. In basic aerodynamics, you learn that wind is always opposite and parallel to the path of the plane. This is true of the main airframe, but not always true of the wings. A moment ago, I mentioned the circulation theory and pointed out how air sweeps up ahead of the wing and produces a downwash behind it. The circulation of air creates a slightly different relative wind for the wings, which is usually inclined upward from the path of the plane. As the angle of attack increases, so does this average relative wind. You have been told that your plane will always stall at the same angle of attack. As you demonstrate a stall on your next biennial flight review, observe the angle made between your wing chord line and the horizon. You know your wing is supposed to stall at maybe 18 degrees, but you are observing 30 degrees. This is because the wing's average relative wind is at a much higher angle than the relative wind for the plane as a whole. In diagram 2, I have introduced a small angle of attack. Note that the average relative wind is also slightly inclined to horizontal. We are still in level flight, so the weight and effective lift are equal and opposite. However, the total lifting force of the wing acts at 90 degrees to the average relative wind. It is now inclined aft and has become greater than the effective lift. The significance of this is that some of the total lift force is now acting toward the rear. It is opposing thrust, so must be classified as drag, induced drag to be specific. How much induced drag is being produced in this instance? We can find that by measuring the distance between the tips of the red and blue arrows. In diagram 3, we have further increased the angle of attack and the average relative wind. Note that the total lift force is at a much larger angle to the effective lift vector and is longer. This situation produces more space between the arrow tips, indicating greater induced drag. Although it may not be completely obvious from our diagrams, the conclusion is that induced drag not only increases with an increased angle of attack, but it also increases at a greater rate than the angle of attack. This is the diagram we used, and you can see that the relative wind for the aircraft sweeps up just before it gets to the leading edge of the wing. As it passes over the wing, a downwash develops and continues behind the trailing edge of the wing. We're not through with induced drag just yet. So far we have dealt only with idealized cross-sectional diagrams of wings. If we put the whole wing together, we will see that the dynamic air does not seem to follow as simplistic a path as in the previous diagrams. The air currents flowing over the wing will take a diagonal path leading toward the fuselage. The currents under the wing will move diagonally toward the tips. Why is this so? It is the nature of liquids and gases to try to fill in any weak spots or holes. We know that the area over the top of the wing has something less than the ambient air pressure. We also know that the air pressure beneath the wing is a bit greater than ambient air pressure, and the higher pressure will try to fill in the area of the lower pressure. Since the wing blocks the passage except for the tips, there is a movement along the bottom of the wing toward the tip. Once there, the air spills up and over, creating a vortex which trails behind and below the tip of the wing. The curling of the air currents over the wing at the tips produces a force which causes the air to be deflected toward the wing roots on the upper surface of the wing. All wings presently flying have tips which produce some amount of vortex. In a vortex, the downwash is greater than the upwash. This situation creates a higher induced angle of attack, which in turn creates higher induced drag. The heavier an aircraft becomes, the slower it flies, the greater the vortex becomes. This means that induced drag is greatest as your plane approaches its level flight stall speed. From your first lesson to your last approach, you have been continually warned to be alert for wake turbulence. Right now, you can probably visualize those twin tornadoes trailing from the tips of a 747. They will drop 800 or 900 feet, level off, and begin to spread apart. Perhaps you have been warned about the big planes so much that you aren't prone to visualize these same tornadoes streaming from a King Air, a C-130, or a Cessna 210. Wake turbulence is generated by all winged aircraft in flight, including helicopters. A good rule to follow is, big and slow, don't fly below. The most successful attempt to reduce vortices and induce drag is the winglet. It was developed originally by NASA and has been utilized by several manufacturers. The effect of a winglet is like an extension to the wing, which increases aspect ratio. A higher aspect ratio diminishes the vortices but does not eliminate them. A diminished vortex results in induced drag. If a designer can reduce the tip vortex, he would lower the wing's average angle of attack, thereby reducing induced drag. There is a way to do this. It lies within the ratio of the wingspan and its chord and is called the aspect ratio. The aspect ratio for a rectangular wing, similar to the ones on many general aviation aircraft, is found by dividing the wingspan by the average chord. A high number would indicate a long, narrow wing, such as those used on high-performance sailplanes. This kind of wing is desirable for aircraft which need, where speed is not an overriding requirement, but climb and cruise performance are. The key to a lower induced drag on a high aspect ratio wing is the distance between the tip vortex and the wing root. Although its effect is felt along the entire wing, the energy of the vortex is dissipated with distance. Theoretically, a wing with an infinite span would have no induced drag. It would be easy for us to assume that a long, slender wing would be the best wing for general aviation aircraft. However, consider that this long, slender wing would be subject to more bending and twisting forces, so it would have to be beefed up internally. The added weight would so reduce performance that there would be no real gain over a shorter wing. There are other reasons as well, one of these being simple ground handling and storage. The designer is faced with one more compromise in putting together the ideal wing for his plane. The formula for determining drag forces is similar to that for lift. Drag is equal to the coefficient of drag times the dynamic pressure times the wing surface area. As in other equations used in aerodynamics, a coefficient is a dimensionless index designed to correct the mathematical process. In this instance, the coefficient of drag is a number which measures how a particular wing develops induced drag at various angles of attack. It would be great if a low coefficient of drag could be associated with the high lift coefficient. Unfortunately, the two increase in value together. We have discussed parasite and induced drag for a while now. Let's see how they compare in their effects on an airplane. Our first consideration is mathematical. Parasite drag varies directly as the speed is squared, while induced drag varies inversely as the speed is squared. The implication is that as an airplane moves faster through the air, the parasite drag builds up rapidly while the induced drag decreases. As the aircraft approaches for a landing, the induced drag increases rapidly while the parasite drag diminishes. A pocket calculator will show how rapidly parasite drag can build. Let's take a plane which develops 100 pounds of parasite drag at 100 miles per hour. We double the speed of the airplane to 200, but parasite drag varies as the square of the speed. This means that now we are producing 400 pounds of parasite drag. Remember that while this is going on, the induced drag has been reduced by the square of the speed. An illustration at this point might help visualize this relationship better. This graph contains the parasite drag curve, the induced drag curve, and the curve for total drag. It is easy to see that as one drag force decreases, the other increases. For practical purposes, the total drag becomes the important curve on the graph. In interpreting this graph, if we assume that the aircraft is producing lift equal to 1g, or the weight of the plane, the lowest point, point A, total drag curve, would give the least amount of drag relative to lift. This point would give the highest lift to drag ratio. The airspeed at the point where induced drag and parasite drag are equal will give this plane its maximum range and also its maximum power-off gliding range. The maximum lift to drag ratio for a given aircraft is established at a fixed angle of attack. On your airplane, the maximum range would occur if you always flew it at the same angle of attack regardless of weight. However, weight will vary, so something must give, and that is airspeed. For maximum range, you would maintain an angle of attack and decrease airspeed as fuel burned off and lighten the aircraft. If you were flying a single-engine aircraft 10,000 feet above the surface and had a power failure, how far would you be able to glide before landing? The answer lies with the angle of attack, which will produce the highest lift-to-drag number. For a hypothetical airplane, a given angle of attack could produce a lift-to-drag number of 10. This is a glide ratio of 10 to 1. You could glide almost 20 miles from that altitude, provided you maintain proper angle of attack. Your airspeed would depend upon the weight of the plane.
The trouble with this idea is that we don't have a good, inexpensive angle of attack indicator. You don't ever know what the angle of attack is at a given time. The best substitute is a chart giving the lift-to-drag numbers at various airspeeds and weights. Most aircraft operating manuals will give a range charts or graphs in the performance section. Although they seldom mention the lift-to-drag numbers, the charts are based on calculations from the lift-to-drag ratios. There are a couple of other figures which you can obtain from a chart of drag curve. A plane's range and endurance are not the same. By slowing the airspeed further, you can keep the plane in the air longer. A rule of thumb might be, if you know the maximum range and maximum gliding range airspeeds of your plane, you can calculate 75% of that figure. You now have the maximum endurance speed. It's pretty slow, but it will keep you in the air longer, if time is more important than distance. No one is going to give you a medal for the most turns made in a holding pattern. The maximum endurance airspeed is at a point where induced drag is creating 75% of the total drag. Keep in mind that it is really a specific angle of attack rather than an airspeed, but for the lack of anything better, we must go with airspeed. One more thing about the airspeed for maximum endurance. It is also the airspeed which will give you the least power-off sink rate. So, for that forced landing due to engine trouble, if your chosen field is under you, you may want the slower speed to give more time for communications and setting the plane up for landing. Certainly you would want to consider minimum sink on a night forced landing. There is another curve which can be plotted on a graph which is related to the drag curve. Although it is overlooked in many basic training manuals and by many flight instructors, the information it presents is very important to those who fly. The graph I refer to is the power required curve, which includes information on the flight in the region of reverse command. At first glance, you will see that the power required curve resembles the curve for total drag. That is only natural since thrust equals drag in order to maintain a given airspeed. However, thrust and power are not quite synonymous. Power is the work turned out by the engine, which it transmits to the propeller, which in turn converts the energy to thrust. In the process, there is some loss of energy, especially at the extremes of airspeed. This is indicated by the power available curve near the top of the chart. The horizontal lines represent percent of brake horsepower, and the vertical lines represent indicated airspeed. The curve begins on the left at the stall speed and ends on the right at the end of the power available line. To the right of the vertical line, through point D, is the region of normal command, or what we call the front side of the power curve. To the left of the vertical line is the region of reverse command, or the back side of the power curve. Consider point D first. It is located at the lowest point of the curve where the power requirement and consequently fuel consumption are at a minimum. This point represents the requirements for maximum endurance and minimum sink glide. At this point, any change in the angle of attack will produce a loss of altitude if power is constant. Point CC is located at the place where a line from the origin of the graph touches the curve as a tangent. This represents the maximum range and maximum gliding range requirements. The significance of this location is that there is a large increase in airspeed at only a slight increase in the power required. At point AA, the pilot is using full power available to maintain maximum airspeed. As at point D, any change in angle of attack will cause a loss in altitude. There is no more power to compensate for a higher angle of attack, so the plane will descend. Lowering the angle of attack will give you increased airspeed, but it will come at the expense of altitude. At any point on the front side of the curve, an increased angle of attack will slow the aircraft and it will climb. A decreased angle of attack will increase speed and cause a loss of altitude. This is what you expect as you fly, and this is why it's called the region of normal command. You will note that for every power setting necessary to maintain a given airspeed on the front side of the power curve, there is an identical power setting required to maintain a much lower airspeed on the back side of the power curve. It is a fact that while in the region of reverse command, the slower you fly, the more power it takes to maintain altitude. This is due to the power of induced drag while the wing is at high angles of attack. Let us assume that the airplane at point C is on a long, power-on final in a busy traffic pattern at an airport with training activities. His airspeed is 73, and he is using 50% of power. Any nudge from his current angle of attack will produce results reversed from normal. Let's suppose this pilot lets the nose drop a little due to some gustiness close to the ground. The airspeed will pick up, but the aircraft's inherent stability will not automatically correct for the extra speed. Unless the throttle is retarded, the plane will momentarily retain the additional airspeed and will climb. Climb with the nose down? That is correct. Remember, we are now in the region of reverse command. Now, let's try to put it another way. The nose of the plane at sea up a bit. The airspeed slows a bit, and the plane begins to sink. The pilot raises the nose a little more and adds some power to regain his approach speed of 73. At this point, 73 is no longer enough. The increased angle of attack has added a large amount of induced drag, which is acting just like a drag chute. The only cure at this point is a lot of power and a lower angle of attack. If the pilot continues to maintain his approach by increasing his nose-high attitude, he will probably mush into the ground short of the runway. It could even happen with the throttle wide open under certain circumstances. Pilots don't get in trouble with the region of reverse command at cruising altitudes because it only occurs at the slower speeds, and these problems are usually on takeoff or landing. One situation which bends a few planes every year is the go-around with full flaps. This is because the flaps have added a tremendous amount of induced drag, and the backside of the power curve has been expanded. It is important in this instance that no climb be attempted until you have determined what a higher angle of attack will actually give you in terms of a climb. Retraction of flaps must be done very slowly and only when there is sufficient altitude to absorb a loss of lift as the flaps come up. Flaps must come up slowly so that the acceleration of the plane has time to compensate for the loss of lift. There is another phenomenon associated with induced drag which can be good or bad depending on how familiar you are with it. It's called ground effect. First, let me tell you what it is not. It is not a cushion of air that forms between the wing and the ground. This myth has been around for many years and has been responsible for many pilots getting into trouble. We discussed previously how updrafts, downdrafts, and vortices form around a wing in motion. You know from that discussion that a portion of the lifting force produced by the wing is directed aft and is referred to as induced drag. As the angle of attack and coefficient of lift increase, so does the induced drag. Induced drag is at its greatest when your plane is slow at a high angle of attack. Suppose that we could eliminate some of the vertical vortices which develop ahead and behind the wing. This would lower the average relative wind and place the chord a little more parallel to the ground. If we could do this, the aft component of lift force, which we call induced drag, would not be as great, but instead would produce a slight increase in the effective lift. That is precisely what ground effect does. If there is no cushion of air, how does this happen? The vertical movement of air around a wing disturbs the air at considerable distance from the wing surface. The vertical distance from this disturbance is roughly the span of the wings. Suppose that your plane has a span of 36 feet and that you're flying that plane 36 feet above the ground. The downwash should have some effect on the blades of grass below you. By descending even further, something has to happen to the downwash. It flattens out because it has no place else to go. The closer to the ground you fly, the more restricted are the vertical velocities behind the wing. At wingspan height, you will lose about 2% of the induced drag. At half the wingspan, you have eliminated about 8% of the induced drag. And when you get down to a quarter of the span, you will have eliminated nearly a quarter of the drag. At touchdown, you will have gotten rid of as much as half of the induced drag. Parasite drag, of course, is hardly a factor at speeds we are talking about. All aircraft encounter ground effect, but it is obvious that the effects will be a little greater on low wing types. However, the difference in location of wings doesn't have a large effect, and the suggestions for flying in and out are similar for all types. We all can remember those student landings when you had everything set up and ready for the flare. Then suddenly the plane ballooned up, the nose pitched down, and you floated and floated. You probably had a little excess speed when you entered the ground effect. With less drag to slow us down, we used most of the runway. No touch and go on that one. If you had a good instructor, he would have taken the time during the taxi back to explain why you had used so much runway. I haven't mentioned the tendency for the nose to pitch down in our earlier explanation of ground effect. Planes are designed to be slightly nose-heavy. The downwash affecting the horizontal stabilizer is used to counteract this nose-down pitch. The purpose of this is for stability, which will be discussed more fully in another presentation in this series. We know then that it is necessary for the horizontal stabilizer to have the downwash in order for it to be effective. In ground effect, the downwash is diminished, allowing the nose to pitch down. This means that upon entering ground effect, you will have to use more elevator. A full stall landing will take considerably more elevator than a normal power-off stall at any altitude. The place where ground effect has caused the most trouble is on takeoff. Most of us were taught to make good use of it during the soft field takeoff. It is also put to good use by many duster pilots and others who regularly fly with maximum gross loads. But for those who don't understand ground effect fully, it can be disastrous. The typical situation is a fully loaded aircraft attempting a takeoff on a hot day. The pilot senses that he is taking more runway than usual, so he horses it into the air at a high angle of attack. He forgets that those first few feet of altitude are high in lift but lower in drag. By the time he is 25 to 30 feet off the runway, some of the original lift has been converted to drag. At this point, the pilot is committed. His runway has been used, and he is 30 feet off the runway behind the power curve. He has no more power to call for and a high angle of attack, which can only cause him to sink. The only real choice for him is to keep from stalling and put the plane down on whatever surface lies off the end of the runway. The elevator response upon leaving ground effect is the reverse of that on landing. Downwash is established as the ground effect diminishes, which puts the horizontal stabilizer back to work. However, you have been using excessive elevator to compensate while you were in ground effect. Upon leaving ground effect, the airplane will pitch up due to too much elevator control. If you were in marginal flight at that time, you could fly right into a stall. The negative consequences of ground effect are quite dramatic. However, you fly in and out of it each time you take off or land. So does everyone else. If you know why it happens and how to deal with it, your landings and takeoffs will continue to be successful. Lift and drag. These are the chief ingredients for the study of aerodynamics. Let's review what we have done. The first thing we did was to define parasite drag and to list all of the elements in its makeup. They were form, skin friction, interference, separation, pressure field, power plant, and wing section profile drag. Next, we spent time analyzing the factors which create induced drag. We compared parasite and induced drag and discovered that when one was weak, the other was powerful. We discussed the wing's aspect ratio and the lift-to-drag ratio. Much of the material in the first part of the presentation became applicable when we discussed the region of reverse command, or what is sometimes called getting behind the power curve. Our final discussion dealt with the lack of drag. It was about ground effect and how to deal with it. This concludes this presentation on the development of drag.
The Beechcraft Barons are not strangers to improper loading. They have a narrow CG range at full gross, and loading variables may provide a pilot an opportunity to enter an illegal flight. Many times, the pilot may not be aware of the transgression. Unfortunately, when the airplane encounters a condition of flight approaching the outside of the design standards, the sudden discovery may be catastrophic. The accident report will carry weight and balance as the secondary cause. This problem is real enough that many pilots have been advised to carry a 50-pound bag of sand in the baggage compartment. We think a simple loading schedule may be a better solution. This tape has 2 sections. The first, a preview of the mysteries of weight and balance by Dr. Wellman, then a pilot operating handbook study of the method used by Beech Aircraft for arriving at the proper loading of a Baron. We will offer a method for constructing a simple graph for a loading schedule that will enable a Baron pilot to decide quickly and easily if planned loading will be within the approved envelope.
When was the last time you gave any thought to such phrases as mean aerodynamic chord, datum, arm, limit load? Hello, my name is Jack Wellman. I'm Director of Program Development for Airmanship Incorporated, the knowledge center for today's pilot. And in this presentation, we'll be talking about weight and balance, and we'll be using those terms. As you progress through this presentation on weight and balance, you'll probably have a few moments of confusion and doubt. Remind yourself that others before you had to figure similar problems without the assistance of the FAA to define terms, or the aeronautical engineers to set the limits for you, or airmanship to put it all together in living color. By the time you finish this presentation, you will rediscover the meanings of the following terms: maximum takeoff weight, empty weight, zero fuel weight, basic operating weight, useful load, maximum ramp or taxi weight, center of gravity, fuel load, mean aerodynamic chord, moment index, datum, arm, moment, limit load, and ultimate load. We will review the concepts of aircraft stability, how the center of gravity limits are determined, and the consequences of an out-of-balance aircraft. Let's deal with weight. Your plane will have designated for it 2 important weight figures. These are the empty weight and the maximum takeoff weight, sometimes referred to as the maximum gross weight. The empty weight consists of the airframe, engines, and all items of operating equipment that have fixed locations and are permanently installed in the aircraft. It includes optional and special equipment, fixed ballast, hydraulic fluid, fuel and undrainable residual fuel and oil. When oil is used for propeller feathering, it's included. Maximum takeoff weight is the maximum allowable weight at the start of the takeoff run. Some aircraft are approved for loading a greater weight, ramp or taxi weight, only to allow for fuel burn-off during ground operation. The takeoff weight for a particular flight may be limited to a lesser weight when runway length, atmospheric conditions, or other variables are adverse. Useful load is the weight of the pilot, co-pilot, passengers, baggage, and usable fuel. It is the empty weight subtracted from the maximum allowable takeoff weight. Some aircraft which have a high fuel burn rate are allowed to load heavier than the maximum takeoff weight. The difference between the ramp or taxi weight and the maximum takeoff weight is the fuel which the crew estimates that the airplane will burn during taxi and run-up. Other aircraft also have a maximum landing weight listed in their operating manuals. This is the maximum weight at which the aircraft may be normally landed. The maximum landing weight may be limited to a lesser weight when runway length or atmospheric conditions dictate. Within the FAA glossary of terms are 2 more weight definitions. Basic operating weight, the aircraft aircraft, including the crew, ready for flight, but without payload and fuel. The other term is maximum allowable zero fuel. It is the maximum allowable weight authorized for the aircraft, not including the fuel load. Zero fuel weight for each particular flight is the operating weight plus the payload. These two terms would be most applicable in the charter and freight divisions of general aviation. Among some pilots, there is an erroneous impression that the maximum takeoff weight is the limit that a plane can lift off the ground. While this may be true under certain conditions of density altitude, it is not the basic reason for a maximum takeoff weight. This limit is determined primarily on the basis of the aircraft's structural design. The wing will only support so much weight. As an example, the FAA requires that all aircraft under 4,000 pounds in normal category must have a minimum limit load factor of 3.8 Gs. The limit load is that factor which an aircraft can repeatedly encounter without creating any structural damage. However, the stressing of an aircraft goes far beyond the limit load. Most general aviation aircraft are designed to accept a force 50% greater than the limit load for one occasion without structural failure occurring. This load factor is called the ultimate load. Between the limit load and the ultimate load, structural damage may probably occur in some form, but the aircraft will not come unglued in one single incident. A chart displayed here is commonly referred to as a VN diagram. On the grid, load factors are represented by horizontal lines and indicated airspeed in miles per hour by the vertical. The area enclosed by dotted lines is what you might call the operating envelope for the aircraft. Radiating out from 1G on the left margin are lines representing gust forces in feet per second. Note that above the 1G line, these gust forces are positive. These positive and negative gusts are related to the attitude of the airplane. On our diagram, we have used colors to illustrate the relationship of this diagram to your airspeed indicator. Point A is the minimum speed at which 1G can be maintained and is established as the stall speed. Lines C, E, and I, G represent the limit load. Structural damage may occur in any area of the diagram which is shaded gray. Maneuvering speed for this plane is located at point C. The curved portion of the dotted line is essentially a continuation of the level stall speed found at point A. Airspeeds less than that at point C cannot produce loads capable of damaging the aircraft. Well, let's suppose that you flew into some turbulence which called for reduced airspeed. You reduce your speed to 100 miles per hour. Suddenly you're hit by an upgust of 30 feet per second. Look at the chart where the 100 miles per hour and the 30 feet per second gust lines cross. The point is outside the operating envelope, meaning that under those conditions you would stall. Sticking with the maneuvering speed for your aircraft will assure you of meeting the limit load while keeping you away from the danger of an inadvertent stall. An aircraft with a maximum takeoff weight of 3,500 pounds will have a limit load of 13,300 pounds based on a factor of 3.8. Now, on a cool day, you could probably get the plane off the ground with a 500-pound overload. However, if you were to hit an upgust, which put a 3.8 G force on your plane, you would be forcing it to accept a full ton more of weight at that instant than it was designed to take. A post-flight inspection should be conducted to locate any wrinkled skin or popped rivets. Repeatedly subjecting your plane to this type of stress may even cause catastrophic failure to occur on some occasion before the ultimate load factor is reached. A negative limit load factor is also designated for all aircraft. It is usually a smaller number except for aerobatic aircraft. Other than down gusts, most aircraft do not receive many really heavy negative G-forces, student landings being the exception, of course. Weight or gravity is one of the four forces acting upon an aircraft in flight. Lift must be greater than weight for an aircraft to get off the ground and fly. The greater the weight, the greater the lift must be to support the plane. If you are forced to produce more lift to support the additional weight, you must also be forced to produce more induced drag. In order to overcome additional drag, you must increase thrust or power. What all this means is that what your airplane weighs on a particular flight will determine to a great degree how much fuel you are going to use. It will affect takeoff performance, cruise, and landing performance. A pilot with an eye towards efficiency will keep his plane as light as possible within the realm of safety. Let us return to a statement we made a few minutes ago concerning maximum takeoff weight. We stated that the maximum takeoff weight was determined by the limit load factor rather than the capability of lifting a certain load off the ground. It is also a fact that there may be atmospheric conditions present which would prevent your plane from getting off the ground even with a load considerably less than the maximum takeoff weight. You know these conditions by the term density altitude. In another tape, we will discuss takeoff performance. But we would like to remind you that conditions of temperature, humidity, altitude, and air pressure must be considered carefully before any takeoff in a fully loaded aircraft. In fact, FAR 91.5 requires that you check all these conditions. It is possible that in several models of general aviation aircraft with all seats filled, baggage at capacity, and full tanks, the maximum takeoff weight may be exceeded. One reason for this is that the FAA has a schedule of standard weights which the aircraft companies use in computing useful loads. The standard weight of a general aviation passenger is given to be 170 pounds. Well, it's easy to see that an aircraft designed to carry 6 170-pounders with full fuel and baggage could be well over gross if you loaded in 6 200-pound fishing companions without offloading some fuel or fishing gear. This information may be useful on the occasion that you want to offload your mother-in-law and put her on an airliner. Also, no two aircraft of the same model will have the same empty weight or useful load. However, all aircraft of the same model will retain maximum takeoff weight. The reason is each aircraft begins a customizing process as soon as it's delivered to its first owner. Each addition or subtraction of equipment, each modification, requires that a mechanic revise the weight and balance records of that particular aircraft. Failure to comply with this requirement just once will throw off all the subsequent weight and balance revisions with perhaps tragic results at some point in the future. Because an aircraft is controlled aerodynamically in flight, we'll take a few minutes to review some of the basic principles of flight. The stability of your aircraft is most affected by the way you balance it. In a general sense, an airplane which is stable will tend to return to its normal attitude unaided after it has been nudged from that attitude by some external force. For example, if you're cruising in straight and level, relatively calm air, a small upgust causes the nose of the plane to pitch up, and a few more pitch oscillations of diminishing intensity will occur until you are once again riding in smooth, level flight. Your aircraft is designed so it has stability in all three axes: roll, pitch, and yaw. When you first look at the diagram of the four forces acting on an aircraft in flight, the diagram probably showed them with lift and weight opposite each other and thrust and drag in opposition. In practice, this is not exactly so, if we discount the download from the horizontal tail surface. Most aircraft are designed so that the center of gravity is actually ahead of the center of pressure, sometimes called the center of lift. The line of thrust is also usually slightly above the line of drag along the longitudinal axis. The offsetting of
creates a situation where the aircraft has a natural tendency to pitch nose down under certain flight conditions. To counter this nose-down tendency, the horizontal tail is set at an angle of incidence which will produce negative lift, a down force. In level cruise flight, at maximum gross weight, your plane should be flying with little or no trim because the horizontal stabilizer is producing just enough negative lift to counter the nose-down tendency of the two offsetting forces. When an upgust shoves the nose up, the angle of attack of the stabilizer lessens and may even go from negative to positive. This causes a reduction in the negative lift of the stabilizer. At this point, the center of gravity ahead of the aerodynamic center will cause the nose to pitch down. After a few seconds of down pitch, the horizontal stabilizer will regain enough negative lift to push the tail down and the nose back up. The pitching oscillations will each diminish in intensity until the tail is once again in balance with the center of gravity. An aircraft which can do this is said to have both static and dynamic stability. Now, let us suppose that in loading your plane with fuel, passengers, and baggage, you have moved the center of gravity beyond the forward limit. The horizontal tail is probably in a fixed angle of incidence and therefore will always produce the same negative lift at maximum gross and level cruise. Since you have moved the center of gravity ahead of the center of lift, you must do something to counter the additional down force of the nose. You do this by using some up elevator. As the center of gravity is moved further forward, you will at some point reach full up elevator in attempting to control the down pitching nose. Beyond that point, no additional aerodynamic control is available, and your plane will continue to dive until it hits the ground. Now, in order to assure you of full aerodynamic pitch control at all airspeeds, the forward center of gravity will be placed at a point which will assure sufficient elevator deflection at minimum airspeeds. Let's change the situation to a takeoff. The maximum downforce from the stabilizer with full elevator deflection is low because the velocity of the relative wind is low. It is possible that the airspeed attained during takeoff will not develop enough aerodynamic pressure with full up elevator to get the nose wheel off in the span of, say, the typical general aviation airport. Landing with an extreme forward center of gravity could cause a loss of control at a critical time. With relative wind slowing and ground effect diminishing the effectiveness of the stabilizer and elevator, you could just simply nose down into the runway out of control. The manufacturer of your aircraft determined the forward center of gravity primarily on the basis of adequate elevator effectiveness at slow flight speeds. Keeping the CG behind the forward limit will guarantee you of up elevator effectiveness. Now, the rear center of gravity limit is based on another concept related to positive stability, meaning the tendency for your plane to return to its trimmed attitude. Your plane has positive stability when it returns unaided to its original attitude. It has neutral stability when it does not return to trim flight but keeps going in the direction to which it was deflected. If the nose is bumped up, the plane will keep going until it stalls. If bumped down, it will dive until it hits the ground. You will be able to control situations of neutral stability. However, a plane with neutral stability will not handle as easily as the one you're accustomed to. In order to get the same thing done, you will have to exert more control force and as a result have a tendency to over-control the plane. How do you keep your plane from becoming neutrally stable? Always make sure that your center of gravity is ahead of the aft limit. Is there such a thing as negative stability? There certainly is. And from the pilot's point of view, it's the worst kind. The center of gravity is behind the center of lift, and there is no tendency for the nose to pitch down. Imagine a power-off stall with the center of gravity behind the rear limit. With positive stability, your plane will pitch down due to the location of the CG. Under negative stability, the tail-heavy craft will tend to increase the pitch up and exaggerate the stall. The action will probably be followed by a spin, possibly a flat spin, from which no recovery technique will work. A few years ago, the FAA General Aviation News published a story about a pilot who lost an airplane
literally. He was flying a small, two-place, low-wing retractable over the farmlands of the Midwest. Suddenly, the engine seized and wrenched itself right from the mounts and fell to the ground. The pilot found himself in one of those hypothetical situations which just doesn't happen. The center of gravity was out of sight behind him. Fortunately, nothing else was damaged, and his airspeed was at a high cruise. He no longer had a need for a hand on the throttle, so he put both hands on the wheel and forced it forward. He had enough airspeed to make it work, and he dove the little bird to the ground at orbital velocity. His flare consisted of a slight relaxation of forward pressure on the controls. The plane bellied into a bean field at a speed greater than his normal cruise. The pilot survived. The plane survived. The engine survived. And all were reunited in about 9 flying once again. This is one of only a few recorded examples of a successful landing with the CG displaced so far to the rear. Most of the time, the results of a tail-heavy loading just leave a mess for someone on the ground to clean up. Negative stability is the worst possible condition you can deliberately place on your plane. Your aircraft is designed to fly with positive stability. You can assure yourself of it staying that way by observing the limits when loading. Now, let's review the consequences of loading an aircraft beyond the limits of the center of gravity envelope. A center of gravity ahead of the limits will, 1, produce excessive stability requiring increased control wheel forces. 2, it will also increase stalling speeds. And 3, decrease performance. A center of gravity too far aft may, 1, reduce control wheel forces with the potential for pilot over-controlling. 2, change stall characteristics from benign to violent. And 3, develop a tendency for a normal spin to become a flat spin. Most concern for balance is centered on controlling pitch along the longitudinal axis. Yaw along the lateral axis also must possess stability, but since loading only affects it indirectly, we will not discuss it further in this presentation. Roll along the vertical axis must also have positive stability. Since most planes have wing tanks and some have nacelle baggage compartments, we'll take a brief look at loading the wings. Most of the optional loading of wings occurs close to the fuselage. It is doubtful that unbalanced loads there will cause much more than a heavy wing, which must be held up either with trim or muscle power. Tip tanks add another. If you fly a plane with tip tanks, fuel management is a necessity. As with elevators, aileron deflection must be limited by design. Full deflection at slow airspeeds may not give you the adequate roll control when tip tank weights are grossly disproportionate. Most aircraft have only one center of gravity envelope developed for them. It is for the longitudinal plane or pitch control. The forward limit is set by the elevator effectiveness at slow airspeeds, while the aft limit is determined so that the aircraft will always have positive stability. In most general aviation aircraft, this envelope is measured in just a few inches of lateral distance. Understanding how to determine the center of gravity for a particular loading situation requires us to review a few terms. The datum is an imaginary vertical plane or line established by the manufacturer from which all measurements of arm or distance are taken. The permissible center of gravity range is measured from the datum in inches. An arm is the horizontal distance in inches from the reference datum to the center of gravity of a particular item. The mathematical sign plus is used for arms located after the datum. A minus sign is used for an item which is placed forward of the datum. Moment is the product of the weight in pounds of an item multiplied by its arm in inches. Moments are expressed in pound inches. Total moment is the weight of the aircraft multiplied by the distance between the datum and the center of gravity. The fuel load is the expendable part of the aircraft load. It includes only usable fuel, not fuel required to fill the lines or that which remains trapped in the tank sump. Gasoline weighs 6 pounds per gallon. Kerosene weighs 6.7 pounds per gallon, and lubricating oil weighs 7.5 pounds per gallon. A station is a location in the aircraft which is identified by a number designating its distance in inches from the datum. The datum is therefore identified as Station 0. The station and arm are usually identical. An item located at station plus 50 would have an arm of 50 inches. The term percent of mean aerodynamic chord, long phrase, is used by some manufacturers to show the limits of the center of gravity. Mean aerodynamic chord is a hypothetical chord line running parallel to the longitudinal axis and is located through the geographical center of the wing. Aircraft manufacturers use several kinds of graphs and charts from which the weight and balance of their aircraft may be calculated. They are all based on what is referred to as the computational method. We will help you with the traditional graphs and tables only in this presentation.
One should watch this presentation before beginning to build a master for another airplane. After watching it, it will be necessary to collect the necessary materials specific to the individual airplane. When the material is organized and the tape is presented, using the pause button on the VCR will provide an opportunity to relate the information on the hypothetical airplane to the actual airplane. You will need to secure the current empty weight for the airplane and the charts and graphs from its handbook. The moment limits versus weight chart, the useful load weights, and moments charts for occupants, the chart for baggage loading, the chart for fuel loading, and the moment limits versus weight graph that will be the template for the matter. We suggest that the graphs and tables be enlarged 8.5 by 11 inch page with several copies made. This will provide more accuracy when these charts are used. The enlarged takeoff weight graph from the performance section of the POH should be mounted on the back side of the completed moment versus weight master for future use. We will discuss this graph fully in a later tape. The complete master loading schedule and the takeoff weight chart may be encased in either a lamination or a sheet protector. If keeping a complete trip record for each flight is useful, 100 loose leaf copies of the master can replace the lamination. A small clear plastic straight edge, a good ink pen, and a pen with erasable ink will be useful for establishing intersection points in the construction of and use of the completed master in flight operations. Beach aircraft tables and graphs remove most of the calculation phase of schedule preparation. We will use these to construct a master that gives a pictorial representation of the loading condition. Following is easy and requires very little arithmetic to operate. The principle is quite simple. At any given station, any weight increases gives a corresponding moment increase. Weight and moment buildup follows a slope peculiar to that station. We will create reference lines each with its own slope for each station. When a line parallel to the reference line from one station is joined at a specific weight point on the parallel line of another station, the new line will lead to a new center of gravity when the desired new weight increases is reached. The basic operating weight in our model that includes the pilot and navigation gear totaling 200 pounds is a constant. All other adjustments may be made by extending or retracting the reference lines if weight deviates from standard. The planning should begin with the occupants being added, then the baggage, and finally the fuel. The primary margin for error with this method lies in the accuracy of the original construction. Our model has broad lines and large dots for camera visibility. The working master should have narrow, well-placed lines and small dots. If the final graph reading raises questions about accuracy on a loading, it should be quickly checked against the tables. To begin the master, the basic empty weight must be current and correct. For our example, we will use a hypothetical 58 with a 3,700 pound empty weight and a 5,500 pounds maximum gross weight. With that information, one turns to the weight limit versus moment table and reads down the weight column to the proper empty weight. The next two columns opposite represents a forward and aft loading possibility. Reading down the forward limit column, we find that this weight has a 2,738 forward limit. The aft limit is 3,182. We will interpolate this to 2960. Turning to the moment versus weight graph and reading up the right side, we find the 3,700-pound horizontal line and hold it while we find the 2,900 and 3,000 diagonal moment line. Between those two, 2960 can be found, and we hold this line with our straight edge and run down the intersection with 3,700 pounds. It is necessary to place a dot here to flag this point to define a line we will draw. We will mark this intersection with a dot. Following the slope of the moment lines to the bottom of the graph, we read less than 80 inches in the bottom scale. We are near the center of the envelope that is an ideal position for the empty weight. Next, we will prepare a scheduled loading, the passengers first. Air carriers may use 180 pounds per passenger and baggage on a 40-60 mix of male and female for their loading schedules. If they are carrying a professional football team or soldiers loaded with combat gear, this may be altered to fit the occasion. We believe that the 170-pound standard adopted by General Aviation is satisfactory except when unusual situations arise. For this illustration, we are loading a club seating configuration, but the charts will conform to any scheduled sanctioned by Beech. Turning to the occupant loading tables, we decide that we will load the pilot at 200 pounds to take care of navigational equipment and the co-pilot, and all other passengers at 170 pounds. The weight column is on the far left of the tables. Reading across to the right, we find provisions for 4 seating possibilities. We will concern ourselves with the front seats for the pilot and co-pilot, the third and fourth aft-facing seats, and the club seating in the rear. Possible cargo loading with the seats removed will require another complete calculation. If this becomes necessary, be aware of the floor loading limitation. Reading across from the 200-pound weight, we find that for the front seats, the moment is 150 forward and 164 aft. Interpolating, we select 155. Back to our graph, we add the 200 pounds to the 3,700-pound empty weight and establish 3,900 pounds as the basic operating weight. Adding the 155 moment to the 2960, we arrive at 3115 as the new moment and place another dot at the intersection. The dot we place at this intersection marks the basic operating weight, or bow, and will be the point of origination of all future schedules since we must always have the pilot on board. The co-pilot's 170 pounds and the interpolated moment of 133 added gives us another intersection requiring a dot. When this is completed, we have loaded the forward seats or crew stations. If we have done our work properly, the 3 dots connected will form a straight line. We can move on to the aft-facing and the club seats and repeat the loading process for each. When we have completed, we will have 3 straight lines connecting 7 dots. Unfortunately, the last passenger has placed the airplane out of CG before we have completed loading. We may have to decide to offload this passenger. Hopefully, our schedule will let us avoid this. We must examine the impact of baggage loading on our problem. To do this, we need baggage reference lines. First, a check should be made of the current 337 form to be sure that no equipment has been installed in the baggage areas that would reduce allowable baggage. To prepare the line, Turn to our baggage loading tables. We note that the 300 allowable pounds in the nose only increases the moment by 45. For our master, we have set the baggage reference lines off the loading plot, but within the envelope to illustrate the point that moving the straight edge parallel to the reference line will enable us to find a new CG without further calculation. We have anchored our model at the intersection of 3,500 pounds and a moment of 2,800. We rise to a moment increase of 2,845, and at the intersection of 3,800 pounds we place a dot. Connect the 2 points and we have a reference line for nose baggage. You may anchor the starting points for these reference lines at a place that seems most convenient for your operation. Repeating the process for 120 pounds and a 216 moment increase for the aft baggage will complete the 2 baggage lines. Note that the slopes are in different directions and that it requires a great deal of weight to have much impact on the nose moment. With the addition of the fuel reference line, we will have completed our master. The fuel offers the most simple concept in the weight and balance standard for the Baron. For our master, we will assume that we may carry 194 gallons weighing 1,164 pounds, and the fuel table tells us this will give a moment increase of 974. This permits us to graph a vertical rise that is only slightly biased to aft loading. We have assembled all the reference lines in our master and have them labeled for instructional purposes. The reference points are easily identified visually, and many people prefer to use this master without the labels. That should be a judgment call of the pilot. Now we may address the problem we have found in our practice loading. Obviously, we must load weight forward. Loading 300 pounds in the nose may be a solution. We find the intersection of the 300-pound increase in weight and the 45 increase in moment and draw a connecting line to the last intersection point, representing the maximum weight for occupants. If there is no desire to use the full 300 pounds, one may take off any desired weight on the line to mark the next departure point. This holds true of any of the reference lines plotted. The 300 pounds in the nose gives us a satisfactory CG range, but we would like to load 120 pounds in the aft baggage compartment. Using the straight edge again, we move the completed reference line from the aft baggage plot up to anchor on the high point of the actual nose baggage line. Rotating it to parallel the reference line will lead to an end point at the 120-pound weight increase line. This brings us to 5,170 pounds if we have used the full 300 pounds in the nose baggage compartment. We have a satisfactory CG range at a zero fuel weight condition. The allowable fuel of 55 gallons plus 4 gallons for start and taxi, our Model 58 is still in CG range, but may be subject to environment before we load the full 5,500 pounds. Another scenario might be a pilot and co-pilot flying metal castings to a satellite plant. They arrive at the airport to find 300 pounds mistakenly loaded in the nose. A quick application of the straight edge anchor on the co-pilot's position rising 300 pounds reveals that the trip is legal until fuel is loaded. Then it is far out of limits. Some weight must be added to or moved to the aft portion of the airplane. The pilot decides to take 120 pounds from the nose and move it to the aft baggage compartment. To do this, he will go up the nose baggage line and establish a new anchor point at the 180-pound increase point. He then rotates to parallel the aft baggage line and rises 120 pounds is found on the right side scale. We need draw no more lines. The visual presentation is clear. We can load fuel to full tanks of 5,534 pounds, allowing for start and taxi, and have a 10-pound overgross condition at takeoff. It should be noted that overloads this small have been mentioned in accident reports. Many flights will be conducted with fuel load rather than passenger load being the primary concern. We suggest that for those flights, a second master be constructed if the graph only requires a single fuel reference line. The line can anchor on the basic operating weight, and further evaluation can begin from the top of the desired fuel load. If this chart is to be used, the two masters may be placed back to back inside a sheet protector or lamination. A pilot using the graph will find it necessary to be aware of the takeoff weight limitations taken from the appropriate chart. This is important enough that it may be advisable to lay down a horizontal line marking the new maximum weight rather than depending on dot placement alone. This will ensure a more accurate loading. We have developed a master schedule for a hypothetical 58 that we can use as a permanent record in any actual flight program. The procedure we use to develop it will work for any Baron. Loading on the different model Barons varies a great deal depending on center of gravity limitations and performance under different conditions. Although the layout looks different on this sample 55 model, the principles are the same. This model offers several possibilities for improper loading, and one must use the proper graph to create the master. You will note that we have placed the nose baggage reference line in the primary schedule after fitting 4 seats. It may be necessary to employ this station frequently, especially if a 5th seat is filled. Loading should also consider the fact that the main and auxiliary tanks lines on this model have different slopes. Auxiliary tanks will have a bad effect on aft CG near the limit, while the mains will help this condition. This may play an important part in the total fuel load, requiring less fuel on board than hoped for. The Baron fuel systems requires careful monitoring to always be certain of total fuel on board. A number of accidents each year attest to this type of oversight. An envelope for the P-Baron also looks different because of the additional weight and accommodations required for the turbocharger installation. Proper weight and balance is particularly important on this model. Takeoff and landing weights and zero fuel weight should be considered for every flight. Each of these is a direct reflection of structural integrity. Although many Baron flights are conducted each day without reference to proper loading, FAA considers it important enough to require a permanent schedule for revenue flights. In the event of an accident, it will determine quickly if the envelope has been broached, and insurance companies may be happy to make the owner very unhappy at settlement time. In normal operations, a pilot will encounter many situations that will require more than an eyeball analysis to ensure proper loading. 60 seconds with a scheduling master may be time well spent. When a pilot becomes familiar with the schedule, it will only be necessary to enter the anchor dots in erasable ink on the plastic sheet and let the straight edge alone lead to the final center of gravity. Beginning at total weight for the occupant stations in most cases is either for calculations for baggage and fuel. Management of weight in the Baron is a very important ingredient in safety of flight. We hope this very functional tool will increase safety in your Baron.
Well, this presentation on weight and balance has taken us through some of the following concepts: aircraft stability, center of gravity envelope, the hazards of loading an aircraft either too far forward or too far aft, reasons for the center of gravity limits. We also reviewed the following terms: datum, arm, moment, empty weight, maximum takeoff weight, maximum gross weight, useful load, maximum ramp or taxi weight, center of gravity, fuel load, moment index. The total fore and aft movement of the center of gravity for most general aviation aircraft is limited to a few inches. For example, a Beechcraft Baron A55 allows for 14 inches between aft limits when the aircraft is light.
but only 6.6 inches when it is at maximum gross. The Cessna Skyhawk allows for an envelope of only about 20 inches at maximum gross. It should be clear from this discussion that careless loading of any aircraft, from an ultralight to a 747, can create problems for the pilot from which there may be little or no chance to recover. Large numbers of flights are conducted each day with 1 or 2 persons on board and only a briefcase and a map case for baggage. The need to calculate weight and balance is remote in these situations, especially when the atmosphere is near standard. However, when the loading of your aircraft involves weight at each station, bulky baggage, cargo, or a gross weight approaching maximum allowable, take the extra few minutes necessary to calculate your weight and balance. It's not only safer, but proper arrangement of weight could save you a few dollars in fuel costs and may get you to your destination a little sooner. We believe you know the consequence for failure to recognize and deal with weight and balance in your aircraft. We hope that this airmanship presentation will bring you greater safety and more pleasure to you as you fly.
The first minute of flight requires that the aircraft enter the flight envelope from the back side, and it must traverse most of the aerodynamic danger points before it reaches a safe speed and altitude. There are no reserves. Total useful energy available must come from the engines, and the energy of motion represents a possible hazard until it can be used as significant lift. There will be no potential energy of position until altitude is sufficient to accommodate a pitch reduction to enter a descending flight path. Possible problems of performance, directional and pitch control, and judgmental errors will be at their worst in this 60-second interval. Unless you're prepared through study and practice, you may experience a very bad day should a problem develop, for there will be no time for deliberation or reflection. You must be right, and right the first time.
Tony Kelly?
Yes.
My name is Dr. Jack Wellman.
Well, nice to meet you, Doctor.
Nice to meet you, sir.
Would you have a seat, please?
Thank you.
Would you like some coffee?
Yeah, coffee black would be fine.
Peggy, would you bring us 2 black coffee, please? Thank you. Well, what can I do for you, Doctor?
Well, I'm not quite sure. I've been giving some thought to getting some additional training in engine out procedures in my light twin. And I thought maybe, I don't know exactly what it is you do here, but I might be talking to the right guy and he could give me some advice.
Is there any reason that you're inquiring at this particular time?
Yeah, an accident. I wasn't involved in one, but an acquaintance of mine was. He was killed and 3 other people were injured in a plane similar to mine.
That's interesting. Could you give me more details about the accident?
Yeah, as best I've been able to understand it, it happened at an airport near my summer home, and I wasn't there, but you know, the word gets around from bystanders and the tower crew people. This friend took off in IFR conditions, 200 feet, mile visibility, light drizzle, and just about the time he got into the clouds, bystanders say an engine sounded rough, and they found the plane about 2.5 miles from the airport boundary. It had spun into the trees, and this acquaintance was killed. 3 others were badly injured. I, of course, didn't see the accident, but I saw the wreckage when they brought it back, and it served to impress me pretty greatly. All this took place in probably about a minute's time.
I see. Well, you know, Doctor, a great many fatal accidents do occur during the first minute of flight, and many of them are caused by failure of flight instruments. Now, unfortunately, a second chance is seldom granted, and we must be right the first time.
Well, I'm increasingly coming to that point of view. I do a great deal of flying around the Great Lakes area, and to meet my schedule at the various hospitals, I have to fly in a good deal of IFR, sometimes from the point where the wheels are coming up to the middle marker, and it's pretty hairy sometimes.
Well, I wonder, do you feel that you could handle a single engine, on instruments, on takeoff, at the present time?
No, I wouldn't bet on it, no.
Well, that's just the point, Doctor. If you're flying under the conditions that you described to me, you are betting on it. The biggest bet that you can make, your life. Now let's up the ante a bit. How do you feel about betting the lives of your passengers as well? You know, the key to coping with the unexpected is mental preparation. In other words, be prepared to expect the unexpected.
Yeah, well, I've heard that before, but how do you prepare to meet the unexpected when by definition it is unexpected?
Well, Doctor, you may also have heard that preparation plus opportunity equals success. You could not be the successful man you are today without years of preparation. Well, apply the same principles to your flying. Just as you must be able to recognize trends in your business, you must be able to detect an event that could lead to an accident if you hope to apply corrective measures in time to change the impending calamity. The mind-hand exercises and playing the what-if game will enable you to take immediate action with confidence. Airmanship's videotape Coping with the Unexpected explains how you can expand and sharpen your ability to handle unusual emergencies. Now, I promise you, Doctor, that I will disclose exactly how you can protect yourself against the mishap that you related to me and others that occur frequently and with equal finality. First, it will be necessary to analyze in detail the events of the first minute of flight. Today, nearly everyone owns or has access to a computer. During this discussion, I will to the ultimate computer, the human brain. The ultimate computer exercises complete control. Nothing can happen without a signal from the master.
Speaking of computers, I just spent 30 grand for a LORAN-C, flight director, and autopilot package. I can fly direct to anywhere I want to go, Tony.
Yes, it's amazing when you think that single-engine aircraft today have more capability than the DC-6s and Connies that we flew the Atlantic routes 30 years ago. You know, there are pilots today who have more invested in black box electronics than they have in the whole aircraft itself. But which one of those devices will come to your assistance if you lose an engine, say at 300 feet? The one that you've owned from birth, the old brain. But as with any computer, it must be programmed to do specific functions. Now, the NTSB, in a special study of accidents following engine failures on takeoff, stated, accidents following engine failures involve a lack of proficiency in responding to these emergencies. And often these accidents involve some degree of panic, probably related to inadequate immediate recall of the exact emergency procedures, or lack of confidence in one's ability to execute the emergency procedures. Now, these symptoms are indicative of insufficient recurrent training in engine failure emergencies. Now, didn't the NTSB say the pilot must program the ultimate computer? And failing to do so could result in panic, freezing at the controls, or doing the wrong thing. To be complete, the training program must have depth. That is, there must be a basic underlying program supplemented with subroutines. The basic program contains a thorough knowledge of aircraft systems, emergency procedures, and pilot skills. The instrument-rated pilot must also meet currency requirements, and he must stay abreast of changes in the FARs and ATC procedures. The subroutine are those conditions which can change with each flight. Some examples are a complete pre-flight inspection, an in-depth weather briefing, filing the flight plan, weight and balance calculations, and a suitable flight log.
Tony, you talk about a basic program. Could you give me an example?
Well, let's suppose we're taxiing to the run-up area. Now, the weather appears to be as reported, about 200 feet overcast and 1 mile visibility. There's a light fog and some drizzle. The wind is calm and the temperature is 5 degrees centigrade. The freezing level was reported to be 4,000 feet over the airport. While taxiing or in the run-up area now, review the takeoff and departure routines. If you were the captain of a crewed plane, you might brief the co-pilot in this manner. I will fly the airplane and handle the power. You will assure that maximum power is available for takeoff and monitor the engine instruments. If you see anything that is not within normal limits while in this segment of the takeoff, call abort. I will immediately cut the power and stop the aircraft. If an engine should fail during segment 2, you will verify the faulty engine and feather on my command. I will maintain airspeed and directional control. Now, Doctor, that is the basic program. Now, it will vary according to the complexity of the airplane and the equipment, but it will apply to all of your departures. Depending on existing conditions, we will supplement that general briefing with additional instructions. For example, I'm talking to the co-pilot now. If an emergency occurs during segment 2, we cannot return to this airport because the weather is below minimums. We will turn right to 175 degrees and proceed to Big Slab Airport. Now, set the ADF and the number 2 nav to Big Slab's runway 15 ILS. In cases you can return to the departure airport, but be prepared in advance if return is doubtful. Have an alternate plan in the old computer, ready to execute. Can you imagine the stress involved in trying to find a suitable departure alternate while on single engine, on IFR, and losing altitude?
But Tony, I don't have a crew.
Well, so brief yourself. You see, it's a key part of the mental preparation for takeoff. Try to anticipate and determine a course of action for any abnormal occurrence. Okay, now let's say you are mentally prepared and you're ready for this IFR departure. You have completed the engine run-up procedures, reviewed your V speeds, are prepared to execute the stored programs for segments 1 and 2, and you have completed your self-briefing. The navs and comms are preset. The anti-ice systems are checked and activated, and the bug is set on the runway heading. Allow me to pause here for a moment to analyze the departure profile. Now, Jack, the FAA has stated that the most likely time for an engine to fail is at first power application or first power reduction. Now, let me give you a sheet of paper so that you can more readily follow what I am about to describe. First, notice that segment 1 does not begin at the departure end of the runway. Takeoff distances and accelerate and stop charts are based on certain preconditions. Now, those preconditions are normally listed on the upper left-hand corner of the chart. The first condition states that maximum power must be applied prior to brake release. Except for very short runways, we normally don't meet that condition. I might add that even though your particular owner's handbook does not state the conditions, the charts are based on full power being applied before the brakes are released. Now, try to determine how much runway that you normally use while advancing the throttles to the maximum allowable power. Then apply computed distances from that point, not from the end of the runway. Now, even so, this computed distance will be minimal because a wet runway, worn brakes, or failure for you to react quickly can increase the distance required to stop considerably. Now, remember, too, that an overloaded aircraft will use a lot of extra runway, and the charts do not compute anything over the allowable gross weight. For example, a 10% increase in gross weight will cause at least a 21% increase in the takeoff distance. Now, the instant that max power is attained, check the engine instruments. The manifold pressure, RPM, fuel flow and pressure. Check the cluster instruments. Be sure that temperatures and pressures are in the green. Check the EGT gauge at full power. Get to know what it looks like. The information it shows can be very, very valuable. Sometimes a partial power loss can be quite confusing, but the EGT gauge is capable of registering that loss. But you need to know what it normally reads at full power. In the event of a complete power loss, the EGT, of course, will drop to 0. If this instrument scan indicates that all systems are go, you are in segment 1 of the takeoff. The computer program for this segment is just one word: stop.
I got to interrupt you here, Tony. I feel when I put full power to my plane, I'm in a go position. I never or rarely ever think of stopping.
Well, Jack, you're just like most pilots, and myself for that matter. But, you know, if you should feel anything, hear anything, see anything, or smell anything that is not normal to that phase, you must stop. Do not rationalize, analyze, or hope that it'll go away. Just stop. Determine the cause before attempting another. You know, it could be something as simple as a seatbelt caught outside the door and banging away, or it might be impending engine failure. You see, you must keep the problem on the ground. Don't be forced to troubleshoot in the air. Look at it this way, Jack. I don't know of anyone who regretted stopping when in doubt. I think all of us know of pilots who wish they had stopped. I'd like to discuss some exceptions, though. We have stated that if anything unusual occurs in segment 1, that we should stop. And for the most part, that is the proper reaction. However, actual conditions may require an instant analysis and a decision to continue the takeoff. Be ready for that possibility. Now, for instance, just as the aircraft rotates on a short runway, the door pops open. Now, if you attempt an abort, the aircraft will surely run off the end of the runway. You make an instant decision to continue. Just keep the airspeeds at normal pattern speed and return to the field. Do not attempt to close the door, especially if you're solo. Now, try to find out in advance if your particular aircraft has any adverse aerodynamic effects from the door being open. Now, for most aircraft, it is minimal, yet every year several accidents, some fatal, are attributed to popped doors.
You know, I remember a while ago, a 421 crashed on departure from, I think it was Aspen in Colorado. The forward luggage door opened, luggage compartment door, suitcases went right into the right prop.
Yes, in this case it was a baggage door that opened, and you know, even if that pilot had feathered immediately, it's questionable if a grossed out twin could have maintained altitude, let alone climb, considering the density altitude where this particular incident occurred. A number of people were killed in that accident. Now, during a training session in which I was to check out several pilots in a Cessna 404, which is similar to the 421, we stopped for some maintenance. And on the very next takeoff, the right baggage door stood straight up just as we reached VMC. Now, since we were in segment 1, the trainee started to reduce the power. I held his hand and we made the takeoff. A quick analysis, you see, revealed that this heavy monster just would not decelerate from this speed on the remaining runway. Also, the door, you know, it has no aerodynamic effect on a 404. So we flew the pattern at nominal speed and made a normal landing. Now, loose items in the baggage compartment remained in place, even some paper towels and things. We departed from the normal program based on a variable event. And in this case, we knew the consequences of making that decision. While training at Ramona Airport in California, for instance, a Baron pilot, he would open his window, his weather window, after each landing to help cool the cabin. It was hot over there. And on one takeoff, he failed to close the window. As we gained speed down the runway, I said, "Hey, Joe, doesn't the sound seem different this time?" And from under his IFR hood, he grumbled. He says, "Yeah, what the hell is that?" And I said, "Hey, Joe, if you don't know, you've got to stop. Don't take this unknown problem into the air with you." And then as we taxied off the runway, I said, "You know, Joe, if you had said, yeah, the weather window's open, and as soon as I can get a hand free here, I'll close it," we could have continued, because you know that a weather window being open has no ill effect on this particular airplane. But you see, Joe, you didn't know that, so that's why you can't take an unknown problem into the air. Troubleshooting belongs on the ground, not in the air. You know, recently, a pilot died, along with his wife and 4 passengers. Witnesses saw the plane's nose baggage door on the right side of the nose come open just as the 421 rotated for takeoff. Although this door swung to its fully open position, no baggage was lost. The pilot became airborne and began to gain altitude. He gained 100 feet, even though the landing gear was never retracted. Apparently, just before turning final, the left prop was feathered. Now, the right engine was not developing power, since the evidence indicated that only 1,000 RPM was being rotated at the time, and the prop was in flat pitch. Now, could he have reduced power on the right engine and then mistakenly feathered the left one? Many pilots have done exactly this while we were in training, trying to recognize dead engines. Again, an open baggage door has no aerodynamic effect on this type of airplane. Could a normal 2-engine pattern and approach to a landing have been made? Well, we may never know, but the evidence would lead us to believe that is so. Now, Jack, that accident in Aspen, Colorado, the fatal accident, probably could have been prevented very easily if the person who had loaded the baggage in the nose compartment had secured it so that it couldn't come out even if the door opened. There probably would have been no accident at all. Now, remember this, segment 1 ends when the gear is in transit. On a short runway, retract the gear just as soon as a positive rate of climb is observed. This will normally be 50 feet or higher. Ever notice your VSI during acceleration? it will usually read 50 feet or so rate of descent while you're accelerating down the runway. Now that's because the air passing over the static ports is not static, but accelerating. And by the time the instrument recognizes a climb, the aircraft is at least 50 feet above the runway. Now on longer runways, leave the gear down until there is no possibility of landing and stopping on the available runway. Now most of the current operators' manuals will recommend this procedure. Oh sure, it's a judgment call, but it's better to run off the runway doing 40 knots than to lose control later and dive in. Now Jack, the common concern, and rightly so, is engine failure prior to a safe single engine climb speed. Now this fear is justified. Very few light twins have the ability to accelerate to a drag condition that will let them climb away safely on single engine. The absolute boundary of safety for these airplanes would be gear in transit or up and VY speed or very near to it. The optimum solution for safety, if these criteria are not met, is still to close the throttles, maintain airspeed to the deck, and hope for a better day tomorrow. Now, if these standards are met, and you know from your pre-flight research that the airplane will in fact climb away on one engine, and that you are able to hack the demands of the next few seconds, then and only then you may decide to go for it. You are now in segment 2. And remember, in segment 2, the program changes. Now, if we lose an engine, we're going to identify, verify, and feather while simultaneously maintaining airspeed and control of the aircraft. Unfortunately, we are through the hazardous zone very quickly. And once VY is attained, an alert pilot should be able to maneuver to a safe landing. Of course, existing conditions must be taken into account. The pilot should know, before initiating the takeoff, whether these conditions will allow sustained flight on single engine. He should have carefully considered the density altitude, the gross weight, the center of gravity, and his own proficiency. Now, if he should determine that departing from an airport with a 7,000-foot density altitude would result in a doubtful single-engine performance, then he must make a rational decision. Now, if he decides to make the departure, he must recognize the fact that it is a calculated risk under those conditions. And then he must take every possible action to minimize the risk factor. He must plan an out or course of action for events that we know have occurred during the first minute of flight. Another tip, whenever you move a switch, a lever, or selector, always check the associated gauge. For instance, throttles, you'd check the manifold pressure. Prop controls, the RPM gauges, and the oil pressure gauges. Mixtures, check the fuel flow and the pressure. Cowl flaps, check cylinder head temperatures, and of course, constantly monitor the electrical load.
I don't understand, Tony, why I should monitor the oil pressure when I reduce the RPM, though.
Well, Jack, on 3 occasions when I reduced to cruise RPM, the oil pressure went below the red line. Now, in each case, some foreign matter had become lodged in the oil pressure regulator, holding it in the open position. Since a fluid, such as oil, is non-compressible, releasing just a little bit of pressure will cause the reading to go to 0. Now, reducing the RPMs reduced the pressure. So increasing to the prior value brought the pressure back into the green arc. And however, you know, if you fail to notice 0 oil pressure for any length of time, you could be in real trouble.
Yeah.
Now, in each case, I brought the aircraft back to the field, had the regulator removed and cleaned, and I was on my way within an hour. Now, upon reaching a safe altitude, you're going to reduce to climb power, and then you're going to increase airspeed to cruise climb airspeed. Now, cruise climb, that is the airspeed, is a variable within certain limits, of course. Now, at full power on the takeoff, excess fuel was delivered to cool the engine. But when you reduced power to cruise climb, and then the airspeed was increased, the airflow replaced the cooling which was previously provided by the excess fuel. Now, in some aircraft, you may know the cowl flaps, but let the cylinder head temperatures be your guide in this case. Now, if no emergency develops, then you can climb away in normal configuration, which you maintain until you reach at least 500 feet AGL. However, there are certain housekeeping chores that you must accomplish, which have a proven record of preventing emergency developments. You must monitor the engine instruments. Don't try to baby the power plants. This is what they are designed to do, and it's better for their health than trying to take it easy on them. Ask any mechanic. He'll give you umpteen reasons to follow the manufacturer's recommendations. Incidentally, Jack, this is a good place to mention the proper operation of switches, selectors, and levers. Try not to flip or change two of them, affecting different engines simultaneously. In the climb, for instance, some checklists call for boost pumps off. Now suppose you operate them together and within seconds an engine acts up or quits. That could cause some degree of confusion, so one at a time. Wait a little bit, then the other one. Much safer. When we approach the problem of emergencies in the first minute of flight, it is usually difficult to categorize areas simply because the narrow time element will transform a simple malfunction into a disaster. Now, aside from the human element, which is always present and oftentimes involves weather, the most common triggers of trouble appear to be instrument malfunctions, propeller malfunctions, and various forms of engines and systems failures. There's something quite unique concerning emergencies during takeoff and the initial climb. You know, Jack, there's no time to consult the handbook. You must be prepared to analyze and execute immediately. And again, you must be right the first time.
Now, earlier you said that the failure of a flight instrument can cause a lot of trouble. Are you aware of any cause where a flight instrument has failed and caused an incident?
Well, sure, we hear of several each year.
Well, what can I do to protect against falling prey to this sort of flight instrument failure problem?
Well, let me explain it this way, Jack. In the early 50s, an airliner departed LaGuardia's runway 13 one dark and snowy night in February. A few minutes later, it crashed on Rikers Island. Prisoners helped pull people from the burning wreckage. Now, a few months later, I was departing from Keflavik, Iceland in the same model DC-6, which the military called a C-118. About the time the gear was tucked in, I had problems holding my heading. If I kept the wings level on the attitude gyro, the compass and turn needle indicated a turn. It almost caused a bad case of vertigo. I asked the co-pilot to take the controls. When he leveled the aircraft with his instruments, I found my gyro doing a slow roll. Now, about a year ago, a Citation SP crashed a few minutes after liftoff into a low overcast. Now, in all of these accounts, the attitude gyro failed at a crucial time during the takeoff. The instrument itself malfunctioned. The pilots followed their erroneous indications to a point that recovery was impossible. Now, I tested this thesis in the military air transport systems simulators. I was an instructor at the time, and now I found that if I placed the aircraft for takeoff on runway 13 at LaGuardia and then rolled the gyro shortly after the wheels were in the wells, even the best military pilots would lose control and crash. Now, after discussing this situation and having them try again, virtually none of them crashed. You see, Jack, they were prepared. Another flight instrument pilots have followed into the ground is the airspeed indicator. During initial training, we're always taught to maintain airspeed during the climb after takeoff. Now, pilots who blindly follow that advice have flown their aircraft back into fatal results. A pilot in my squadron in the Air Force his landing lights because the light fog was reflecting them back into his eyes. And then, without thinking, he tried to maintain his relationship to the retracting beams. Well, he flew the ship back into the runway. Now, although the gear was still down, there was substantial damage and a few injuries. You know, a bug flying into the pitot tube, ice, or a failure of the system can cause an erroneous airspeed reading. But you can protect yourself from following it to destruction if you are prepared. Now, the third instrument to consider in this critical triangle is the gyro compass. Although it's not as critical as the other two, a failure during the first minute can cause confusion, and if not correctly and quickly analyzed.
Oh, excuse me here. I had a compass fail on me in broad daylight, not on takeoff, and it was confusing enough. I don't know what would happen if I had one fail on takeoff.
Well, in most complex singles and light twins, each of these instruments is powered by a different power source. And the airspeed is activated by the pitot-static system, the attitude gyro by the air or vacuum system, and the compass by DC electric. Now, the odds that two power sources will fail simultaneously are astronomical. One source may fail or an individual instrument may fail. Now, since these failures do happen and since they often result in a fatal accident, we must be prepared with a computer program ready to put into action. Now, Jack, let's talk about an instrument departure where you, the pilot, are mentally prepared for failure of one of the flight instruments or one of their power sources. Now, our instrument scan begins just at liftoff in our complex single or light twin aircraft. We need only concern ourselves with 3 instruments during the initial climb to a safe maneuvering altitude. Now, this group has been dubbed the critical triangle of agreement. Since we are reviewing only 3 tightly grouped instruments, we can consult them more often, thereby keeping the tolerances much closer. Okay, we have just lifted off. Remember, we always place the bug on the runway heading. Now, just like the airliners, pitch to an attitude. Of course, we must determine what this attitude will be by observing the degree of pitch on the attitude gyro with gear and flaps up and maximum continuous power applied. We should retract the gear when a positive rate of climb is noted and allow the airspeed to stabilize at the best rate of climb speed. Now note the nose up pitch attitude in this stable condition. Smoothly pitch to this attitude after reaching computed liftoff speed or VMC plus 5 knots, whichever you like best. The aircraft will always seek the target airspeed. Remember, power plus attitude equals a predictable performance.
Tony, which of these flight instruments do you consider the most critical?
Well, Jack, my experience would indicate that the attitude gyro is the most likely of the 3 critical instruments to fail during the initial climb. Even more so in single-engine aircraft because a vacuum pump failure often is the reason that the gyro rolls over and plays dead. So let's see how we might handle this often disastrous failure. We're about 300 feet with the gear in the wells and on the gauges. The attitude gyro begins a slow roll to the right. Now initially, we follow an attempt to keep the wings level. But look, the bug is moving away from the lubber line. The compass is indicating a slight right turn. Now we have an argument, a disagreement among our 3 critical instruments. Now that's intolerable. We can't allow that even for a few seconds. We must settle this argument immediately. To do that, we will need the applied authority, an arbitrator. Now in this case, the turn indicator. If it is indicating a turn, it is voting for the compass. If not, it tells us the compass is a guilty one. Today, it indicates a right turn. The attitude gyro is lying. Right now, stop the turn. Level the wings and climb out on partial panel. You must now revert to the airspeed indicator to maintain pitch angle. But remember, we've already determined the relationship between the airspeed and the pitch shown on the attitude gyro, and we can now be sure that power and airspeed will result in the correct climb attitude. A little practice will make you acutely aware of these relationships. Again, the key is to be mentally prepared for this contingency prior to taking the runway. Now, the next instrument that's most likely to fail during the first minute is the airspeed. Even though you check your pitot heat during the pre-flight and turn it on before takeoff, you cannot be sure it's operating when you encounter ice, say at 1,000 feet AGL. A simple light or a gauge would do the trick, but unfortunately, none is installed in our business aircraft. Well, at any rate, malfunctions can be due to other causes, such as obstructions or failures within the system itself. On one occasion, the plastic tube leading from the pitot head to the instrument came off at liftoff, resulting in an immediate 0 indication.
But Tony, how do we handle these failures?
Well, Jack, the most difficult to recognize and react to quickly is the gradual reduction in airspeed. Now, ice will usually cause this, and ice will generally form on the unheated pitot mast before it's visible anywhere else on the aircraft. Let's go back to the 300-foot point at this time and assume an airspeed failure. Now again, we are scanning only the 3 critical instruments. So far, all is well. The gear is up, and we're climbing away at V1 speed. Uh-oh, the airspeed's beginning to back off. Better lower the nose a little bit. The airspeed's still backing off. Now be careful. Don't lower the nose below the horizon. Stop at about 3 to 5 degrees climb attitude. Well, we have an argument again between our 3 critical instruments. We must settle this argument. Now again, we'll consult an outside authority. This time our arbitrator is the VSI. We have noted on normal departure climbs that the VSI indicates about 1,200 feet per minute at maximum continuous power in this configuration. Now, since we have depressed the nose of the aircraft, it is now indicating only 300 feet per minute. Again, a warning, Jack. Do not allow the VSI needle to indicate a negative or descent. Again, power plus attitude will result in a predictable performance. We have settled this argument in favor of the attitude gyro. Go back to the normal pitch attitude and stay on the bug. You're not in any danger if you never allow a negative pitch angle or vertical speed indication, and if you keep the wings level. Continue the climb. Disregard the airspeed. And when you have time, double check the pitot heat switch and the circuit breaker. Now, in some aircraft, such as Beech Barons and Bonanzas, the circuit breaker is in the switch itself. It's called a switch breaker. Wait a few minutes before trying to turn this type of switch back on to allow for cooling. Jack, you can practice for this contingency by covering the airspeed indicator on VFR climbs. And you might want to check the pitch attitude while using various combinations of power and speed, such as the one you use for cruise climb. Mentally prepare for the possibility of airspeed failure on takeoff. Don't allow any event to surprise you.
I think I'm finally beginning to understand how to prepare for the unexpected.
Jack, it's really just a mental attitude, but it must become an acquired habit. Speaking of airspeed failures, allow me to relate an interesting experience that happened to one of my clients. His aircraft, in this case it was a V-35 Bonanza, needed a pitot-static check before we could complete the training. And the check was completed at a nearby airport, and the pilot picked up his plane just at dusk to fly it back to the Palomar Airport. Now things began to combine in a conspiracy against this pilot. First, the light was fading, and secondly, the technician had used a clear tape to cover the static ports. Now, this pilot did not remove the tape, the technician did not remove the tape, and then the pilot did not see it because of the failing light. On the takeoff, the aircraft was too far down this short runway to abort when the pilot noticed the airspeed had barely left the peg. Well, he rotated and he retracted the gear and started the climb. Then he noticed that the VSI was still reading 0 and the altimeter was at field elevation. "What did you do?" I asked him, and he proudly answered, "Why, I flew it around the pattern and landed without the instruments." "Did you consider selecting the alternate static source?" I asked. And he said, "Well, Tony, now that you mention it, I must admit the thought never entered my mind." Now, the point to be made here, Jack, is that even a little stress degrades the thinking process. I've posed this same problem to many pilots in the classroom, and surprisingly, about 80% say they would return and land without the instruments. You know, some don't know where the static source selector is located, nor what effect it will have on the instrument readings. Now, one fellow who flies a pressurized aircraft thought that the static drain valve was the alternate static source. Now, can you imagine what would happen if he turned that valve while in pressurized flight with the altitude hold engaged?
Well, to be honest, Tony, I'm not that familiar with pressurized aircraft. What would happen?
Well, briefly, Jack, the pressure from inside the aircraft would now back up through the static system and probably blow all of the aneroids in the flight instruments. And if the altitude hold was engaged, it would immediately and very quickly and abruptly try to seek the new altitude that would be indicating on the altimeter. But you know, Jack, most instrument-rated pilots would recognize a failed gyro compass before getting into an uncontrollable attitude. Sometimes the gyro compass will spin rapidly, other times it will just freeze in place, and the pilot wouldn't realize it had failed until he tried to make a turn. A slow turn, that is, the compass turning slowly, would be the worst case. Once again, the turn indicator will determine if the aircraft is actually turning. Cover the directional gyro on VFR climbs and practice making timed turns as part of your mental preparation against this kind of malfunction. You'll find that with just a little practice and serious thought, you should not fall prey to any of these flight instrument malfunctions. But let me give you a little tip. Should a flight instrument fail, cover it up. This will prevent knee-jerk reaction every time you look at it. Now, a propeller malfunction, whether on takeoff or in flight, can be a most unpleasant experience. Let's take a look at one or two possibilities. Several times each year, propeller blades fail in flight. Sometimes a complete blade flies off, and other times only a piece breaks off. In either case, a severe unbalance is created. The engine can be torn from the aircraft in a matter of moments. And the best action in this case is preventive action. Try to prevent that from ever happening by proper maintenance of your propeller. It is difficult to analyze the problem and react in time in the air, especially on takeoff. The symptoms of blade loss is severe vibration. Immediately go for the prop lever and attempt to feather. Even if the condition had another cause, severe vibration is a heck of a good reason to feather. In those cases where the engine was torn from the aircraft jack, it was impossible to fly the plane. The change in the center of gravity, along with the asymmetric drag and thrust, were beyond the capability of the flight control surfaces. In that unhappy event, the best anyone can do is to reduce the power on the good engine and try to glide to a landing. There are reports of the entire propeller leaving the plane. This can be handled by promptly shutting the engine down. A few years ago in Florida, a twin pilot had to take evasive action when the separated propeller circled back toward his plane. He landed safely without damage or injury, but imagine being attacked by your own airplane in flight. You know, just last month, I read an accident report relating to an airplane crash because the elevator trim tab action had been reversed. Never be more careful than when accepting an aircraft after maintenance has been done. You may well become an unwitting test pilot. Aileron action has been reversed with equally fatal results. We sometimes grow complacent and perform pre-flight and before takeoff checklists in a very perfunctory manner. Yet we should never be more aware of what we see, hear, feel, or smell. Airplanes talk to us constantly, but the language, Jack, is very subtle, and it requires interpretation on our part. Sometimes, such as just after liftoff, little time is available to ponder the message. Some knowledge of the language can hasten any action demanded by that communication. And we all know a pilot who, after experiencing an unhappy incident, has said to everyone, "You know, I noticed whatever it was during the last several takeoffs." But no preventive action was taken. He waited until the event he was warned about actually occurred. When last time you had a talk with your airplane? Now, let us examine some facts relative to preparation for the Go For It program. You have VY speed and the gear is up or coming up. Now, your mental computer program is identify, verify, and feather, and above all, maintain heading and airspeed before, during, and after accomplishing these mandatory items. This will be very likely the most important mental and physical exercise you will accomplish in your entire lifetime. Now, how about reducing power to verify the dead engine and then feathering the other engine? You know, it happens regularly during training. Unfortunately, this is an irreversible action. Now, first, let me state that I have not found a single pilot in 30 years of instruction who has consistently recognized the dead engine by using dead foot. Not one. Since that may be the beginning of a chain reaction leading to disaster, let's do something about it. Why rely on just one sense? In this case, it's the sense of feel. We can enhance the message by introducing another sense, sight. Remember we suggested the bug be placed on the runway heading? When an engine quits abruptly, it is almost impossible to hold the heading. There will be some deviation. The lubber line, or nose of the aircraft, will move in the direction of the faulty engine. Also, we recommend checking the EGT gauge at full power. The reading will immediately drop to 0 when the fire goes out. Now, don't disregard the dead foot entirely. Use it to confirm your visual cues. If the bug and the EGT agree that the right engine has failed, then tentatively raise the right foot just a bit. Okay, there's no change in heading, then all three indications are saying the same thing. And yet, we still verify by reducing power on the right engine. Now, it's at this point pilots make a serious mistake. Yeah, they feather the wrong engine. Now, here's a procedure that may help you from making that kind of mistake. When you lift the dead foot from the rudder pedal, raise the first 2 fingers of your throttle hand. Now bend down either the right or left finger corresponding to the foot that you lifted. Now, if you place these two fingers over the throttles and pull back, only one throttle will come back, the correct one. Now, if you do the same thing to the prop controls, again, you will come back, only one will come back, and it will be the correct one. Now, the thinking process has now been eliminated. Pure mechanical action does the job for you, and it does it correctly. But practice this procedure until you can claim it as yours. Remember, even a little stress can cause trouble with the thinking process.
Well, if you've got a minute or two, Tony, I'd like to have you explain to me how I might be able to increase performance or safety when that engine fails in segment 2.
Yes, Jack. Well, first you should realize that speeds quoted in your operator's manual, such as VMC, VY, VX, VYSE, and VXSE, are all variable, even though only one value is given in the manual. Knowing that these speeds vary can allow you to obtain the optimum performance under varying flight conditions. Only two speeds are noted on the airspeed indicator for ready reference. The VMC is depicted by a red line and the VYSE by a blue line. But the actual VMC and VYSE speeds are rarely the same as seen on the airspeed indicator. Now, jet aircraft, for instance, use a movable reference bug to allow for the variable conditions, thus the reference to bug speed or VREF speeds. By the way, Jack, do you know what the VM is on your airplane?
Yeah, my plane, it's 80.
80 knots.
Mm-hmm.
The VMC shown in your manual was obtained under a given set of circumstances. The aircraft was at gross weight, CG at the rear part of the envelope, the gear was up, flaps in the takeoff position, dead engine windmilling, and the good engine at full power, and a 5-degree bank was established into the good engine. So in some cases, the actual VMC could actually be lower than the book value, and at other times, considerably higher. Now, it's to our advantage to keep the VMC as low as possible. But you know, it's very possible to get the VMC up around 130 if you're not careful. Most people don't realize that. Now, we can help greatly by immediately doing the following. Maintain airspeed and heading and establish a slight bank into the operating engine. That'll keep your VMC as low as possible. If the wings are held level after power is lost on one side, the result of the asymmetric thrust and rudder applied to maintain heading cause the airplane to slip through the air sideways, a side slip, if you will. If you tape a piece of yarn to the nose of your ship, you can observe this slip. The yarn will flow toward the operating engine in level flight. Allowing a twin with asymmetric power to side slip results in two negative effects. One is the drag resulting from moving sideways through the air. Remember, slips are often used intentionally to create additional drag during an approach. But when a twin is flown on one engine, performance may be so anemic that the additional drag created by an unintentional and certainly unnoticeable side slip can make the difference between being able to climb or descending to the ground and making contact with the ground. Now, the other disadvantage is not quite so obvious, but is also curtailed. Some of the relative wind, which approaches the airplane from the side, pushes against the vertical stabilizer. This compounds the problem of directional control because it adds to the effect of the asymmetric thrust. Hence, both forces are now trying to yaw the airplane toward the dead engine. Consequently, the rudder must apply a greater force to keep the airplane pointed straight ahead. But lo, the amount of rudder control has actually eroded. Now, this is because the vertical stabilizer prevents some of the relative wind from striking the rudder. It shields it a bit, decreasing control effectiveness of the air that does contact the rudder. Now, the air that is contacting the rudder is contacting it at a smaller angle. This is further reducing the effectiveness. The accumulative effect is to increase VMC. Now, to keep the VMC as low as possible requires proper handling of the crippled twin. We must eliminate the negative effects caused by wings level side slipping. This can be accomplished by banking the airplane toward the operating engine and thus tilting the direction of the wing lift. The resultant horizontal component of lift acts to oppose the side slipping force produced by the rudder. Now we have stopped the side slip by using about 5 degrees of bank into the good engine. The relative wind is now lined up with the longitudinal axis of the aircraft. We have eliminated the adverse effects of the wind striking the vertical stabilizer, and a greater amount of air contacts the rudder at a larger angle. The resulting increased rudder power allows directional control to be maintained at a slower speed. In effect, we have lowered VMC. How important is this? Well, studies show that if some types of twins are into a dead engine, it may be impossible to recover. The VMC just keeps increasing. Full control movements are used to correct the situation. The typical VMC roll is followed inevitably by an uncontrolled encounter with the ground. The 5-degree bank also improves aerodynamic performance. The plane can be flown at a slower, more efficient airspeed, at or near the blue line instead of above it. The power that had been overcoming the drag caused by the side slip can now be made available for the climb. You know, I have witnessed aircraft double their single engine rate of climb by assuming the proper attitude. A word of caution: don't overdo a good thing. An excessive angle of bank degrades the climb performance, so the FAA allows the manufacturers to publish the VMC resulting from no more than 5 degrees of bank into the good engine. Now, you know, even though it's a mere 5 degrees, it may seem insignificant, but it does have a profound effect. A 5,000-pound aircraft is developing 5,000 pounds of lift in level flight. When the aircraft is banked just 5 degrees to the right, the horizontal component of lift exerts a force of 436 pounds horizontally. This force is helping the rudder do its job. So now we can relax the rudder pressure a bit. The vertical component of lift is hardly affected by this bank, and it still exerts about 4,981 pounds, a mere 19-pound loss in lift. Now, if you have trouble remembering, as many people do, which engine to raise, just think, raise the dead. To further emphasize the importance of proper flight attitude, that is, bank angle, airspeed, and directional control, consider these facts. The VMC can increase as much as 3 knots for each degree of bank. VMC was established with 5 degrees of bank into the good engine. So with wings level, the VMC could already be as much as 15 knots faster than the book value. An unintentional bank of 15 degrees into the dead engine could raise the published VMC by as much as 60 knots. Now, we won't have that kind of excess airspeed on climb out, so we are several knots below the actual VMC within seconds. Recovery is unlikely at this altitude, and the best we can do is to reduce power on the good engine and hope to contact the ground under controlled conditions. Now, instincts tell us that we need more power under these conditions, so many aircraft hit the earth while developing full power on the operating engine. But aerodynamically, the facts are even more deadly. Now, that's because the increase in VMC is not linear, but can snowball rapidly and become uncontrollable. Now, Jack, we just learned that VMC is a variable speed. Well, so is VYSE, or the best single engine rate of climb. Incidentally, do you know the best single engine rate of climb in your aircraft?
Yeah, mine is 115.
115. Well, you know, most manuals do not acknowledge the fact that this is a variable speed. They just give 1, such as it did in your manual. But some do, and as an example, the Cessna 414A manual has a tabulated block on the 1-engine rate of climb chart, as we're showing here. It tells us that at gross weight, 6,750 pounds, the best single engine rate of climb is 108 knots. Now, that's blue line on your airspeed indicator. But it shows at 6,250 pounds, 105 knots is recommended. And at 5,750 pounds, we should fly at 102 knots to get best rate of single engine rate of climb. Now, that's a reduction of 6 knots at 1,000 pounds under gross weight. Now, even if your manual does not display this data, as a rule of thumb, a reduction in indicated airspeed of 1/2 knot for each 100 pounds under gross weight will usually produce an optimum single engine rate of climb. Now, in addition to that, non-turbocharged aircraft can reduce VYSE, that is single engine rate of climb, by another 1/2 knot for every 1,000 feet above sea level. So although the blue line is a good target speed to hold while cleaning up the aircraft, you may be able to coax a few more feet per minute rate of climb by applying these rules.
Well, could I have an example? I'm having trouble getting it into my mind on how that works.
Yes, Jack. I just gave you a rule of thumb if the data doesn't happen to be in your handbook. But let's take a look at an actual example from a typical light twin handbook. The blue line, or VYSE, is 106 knots at gross weight. Now, if we're departing a 5,000 foot above sea level airport, 400 pounds under gross weight, the best single engine rate of climb is 96 knots. A 4-knot reduction for weight and another 6-knot reduction for altitude. Sometimes, using this reduction in VYSE can mean a significant increase in the single engine rate of climb. Now, we still have one more unknown factor, Jack, and that is the airspeed indicator itself. Have you noticed that there is no requirement to have it calibrated at regular intervals? Well, then how do you know it's accurate? You don't. So at some time, maybe you should carefully calculate the weight of the airplane, get some altitude and feather an engine. Then in smooth air, deliberately experiment until you find the best rate of climb. Then apply the variables, altitude, and plot a chart which will approximate the best speeds for the various conditions. I've been asked what effect weight has on VMC. Well, normally I don't consider weight as important as some other factors, but it does affect VMC, and you can plot a chart that will indicate this effect. When the lift component is leaned over 5 degrees and a line is dropped from the tip of the lift component to intercept a horizontal line from the longitudinal axis of the aircraft, a triangle is created. And the heavier the aircraft, the longer the lift component will be. Now, a longer lift component then will result in a longer horizontal component, and that will result in a lower VMC. But I give much greater credence to the effective center of gravity, for instance, on VMC. The further forward within the envelope the CG is located, the lower the VMC. Now that's because we lengthen the lever to the rudder itself, giving it greater leverage to control the yaw. So for the takeoff, have your passengers sit as far forward as possible and stow all their loose gear in the nose compartment. They can move to a seat near the rear if you have, for instance, club seating. They can move to the rear seats after you're in level flight in cruise conditions. Now consider this situation. As an airplane on one engine slows down in flight, here's a pilot who's trying to maintain altitude, and he slows down. The P factor causes the thrust vector to move further and further out from the fuselage. Now we're assuming that the critical engine is the one that's feathered and that we don't have counter-rotating props, which is the case with most light twins. The rudder will reach full travel much sooner, and VMC is thereby increased considerably. So again, maintain your airspeed and directional control. Very important. Too often pilots do let the airspeed get too low, mostly because of distractions, and there are a lot of them at a time like that when you lose an engine. And then to correct the yaw, they crank in a whole bunch of aileron. It's a natural instinct, but don't succumb to it. Use all of the rudder before using much more than just about a quarter of aileron.
Yeah, but why is that so?
Well, this is because you might induce a stall on the wing that you're trying to raise. Suddenly the airplane rolled to the left and dived straight into the ground is the way the witnesses described the crash. Now, if the wing is close to the critical stall angle, as it very well might be at low speed on single engine, then full aileron could increase the angle of attack on that side and induce the stall. So instead of raising the wing stalls and the airplane begins a spin to the left. Read the accident reports, Jack. You can pick out that kind of accident at any time. Now we said, Jack, that VXSE, or obstacle clearance speed, was also a variable. Well, it is, but it increases with altitude at half the rate that the VYSE decreases. Don't ever plan on using VXSE. Remember, it's an emergency speed, but know what it is in case of an emergency. Sometime while training, an instructor may ask you to perform a VMC demonstration. Be very careful. This is a potentially disastrous maneuver, especially for a high-powered aircraft. Now, consider a twin flying on single engine. The induced airflow from the high power of the good engine creates a considerable lift. Much less lift is being developed on the dead engine's wing. Now, this causes a rolling tendency, which we can normally control with rudder and a little aileron. When we're flying on single engine, now we have two stalls to contend with. The power off stall speed may be much higher than the power on stall speed, and so will occur first. As the airplane slows for this VMC demonstration, we're waiting for the full rudder application. Then, as the nose yaws toward the dead engine, we drop the nose and reduce power and make a recovery. But if the VMC is below the stall speed, then the stall will occur first before we run out of rudder. As we slow the aircraft, the elevator control is increased. Now, Jack, the thing we have to be careful of at this point is a snap roll. The aircraft could very easily enter a snap roll because we have all the ingredients present. Now, remember, a snap roll is performed in an aerobatic aircraft by pulling all the way back on the stick and pushing in full rudder. Now, in your high-performance twin, which is not an aerobatic aircraft, the power-off wing will stall first. Suddenly, there's no lift on that wing, while maximum lift is still being applied to the power-on wing. Now, in addition, the aft elevator and rudder complete the requirements for a horizontal spin or snap roll, and your aircraft could very quickly enter a number of different maneuvers, none of which the aircraft has been approved for.
You mean my airplane has never been spun and tested to see what happens in a spin?
That's correct, Jack. Twin-engine aircraft are not spin tested at the factory, and no one really knows what will happen if they should get into a spin, so we must avoid that at all costs. Now, a quick reaction by the pilot may result in stopping this snap roll action with the aircraft upside down in a stalled position. Now the good engine will be starved and it will stop. And in many cases, witnesses report seeing the aircraft spinning down and then striking the ground, tail first. Now this chart depicts the VMC stall relationship in a typical light twin training aircraft. With normally aspirated engines, the VMC decreases as the power decreases with altitude. Now, Jack, the FAA does not clearly distinguish between training aircraft and high-performance aircraft. Now, it's probably perfectly safe or safe enough to do a VMC demonstration in what we normally refer to as light twin training aircraft. In some light twins, the stall speed is higher than the VMC at sea level. Since the engines are normally aspirated, the difference grows larger with altitude, and the stall will always occur first. Many turbocharged airplanes' stall speeds and VMC are very close from sea level all the way up to the critical altitude.
Well, should I perform a VMC demonstration in my plane?
Well, Jack, my advice is never to perform a VMC demonstration in a high-performance twin aircraft. You see, although most pilots are aware of the danger, it may still be a required maneuver on a rating ride, and it should be approached with extreme caution and understanding. I think all veteran pilots have lost friends and acquaintances to this demonstration, which has virtually no margin for error from the student or the instructor. Now, we've had the mental preparation for the go for it phase of segment 2. Now let us look at the execution of actions designed to save your skin. You must remember and execute the mandatory items for engine failure, which are, in segment now, identify, verify, and feather. Now, you have practiced lately with a very good instructor, and you're able to hold your heading and airspeed while your little cockpit world is falling apart about you. Your static airplane cockpit practice has enabled you to find and correctly position the fuel shutoff mechanism every time without taking your eyes off the flight instruments. Okay, you are ready. Now, I might inject a word of caution here, Jack. Before takeoff, decide on a minimum altitude below which no restart will be attempted. Now, you can expect to sacrifice some altitude while performing these actions. And personally, I would not attempt a restart below 500 feet AGL. Now, the most common cause of engine failures is related to the fuel system. Let's take a typical case where we have a fuel system problem on takeoff. Okay, the first thing is to identify the faulty engine. Number two would be to decrease the throttle to verify that that is the faulty engine. Number three, we will check the fuel flow or the fuel pressures. Then let's take a good look at the fuel gauges to make sure that they are indicating that we have some fuel. Now, the fuel selector, it's possible that it has got kicked to the off position. So either make sure it's in the proper position or switch tanks if switching is possible. Turn the boost pump on in case it was an engine-driven fuel pump failure. And then try adjusting the mixtures. Now, easing the throttle back to verify the faulty engine served another purpose. Should the engine restart, there is less chance now of a temporary overspeed condition. In many cases, the engine will restart. Any of the actions that we have taken here could resolve the problem. If not, then check the magnetos, the second most likely cause of ignition. If a restart is not possible, then go ahead and feather the engine. You know, the third most likely cause of engine failure is mechanical. Modern engines are remarkably reliable. Less than 10% of engine failures are caused by actual mechanical breakage when the engine is properly maintained. The most likely time for a mechanical failure is during the greatest stress time, which is on takeoff. This failure can take many forms: abrupt and complete, partial power loss, surging, loss of engine parts, oil loss, and fire. For the most part, the engine cannot be made to run again normally after experiencing a mechanical failure. Now, let's take a look at a mechanical failure. In many cases, a mechanical failure will cause an abrupt and complete loss of power. Use the basic engine failure program to begin with, which was identify, verify, and feather, while maintaining airspeed and altitude continuously and simultaneously. Now, if you have a partial power loss or a surging engine, of course, you're going to be able to identify that engine quite readily in this case and reduce the throttle on that engine. Sometimes that will smooth it out and you'll be able to get a little bit better power from it. Now, let's climb. As long as the engine's producing some power and it's not on fire, let's climb at least VY speed and get some altitude. Now, upon reaching a safe maneuvering altitude, troubleshoot the engine. Conditions permitting, land with the engine running. Even though it's rough or surging a little bit, keep it running. Now, if none of that works, then go ahead and feather the engine. If it's too rough and nothing smooths it out, go ahead and feather the engine and make a single engine approach and landing. We've conditioned ourselves to expect an engine failure, but we must prepare an out, an avenue of escape.
An avenue of escape. What do you mean by that?
Well, Jack, let me put it this way. Last summer, we were training up at San Luis Obispo, California, in a B-58 Baron. Now, fairly high terrain surrounds the entire airport. The pilot told me that during the winter, fog covers the area most of the day. It's usually only about 1,500 feet thick, but if an engine failed during segment 2 of the takeoff and you were on instruments, there's a good chance that the unprepared pilot would fly into the high ground because single-engine rate of climb would not permit clearing the hills.
Mm-hmm.
Well, just north of the field, Jack, there was a river, and it runs down to the ocean. So we timed a few takeoffs using blue line speed, and we found that it took, X minutes to reach the river. Then a turn of X degrees to the left, and we followed the river down to the ocean. Now, once over the ocean, which is at sea level, of course, we could gain some altitude before proceeding back inland to a pre-selected airport. Now, can you prepare such an avenue of escape at the airports that you frequently use? Give it some thought. Now, let's consider the most dreaded of the engine failure emergencies, an engine fire. Now, here is a general checklist. I must say at this time for all of the checklists that we're using here that they are general, that you should be familiar with the checklist in your handbook. But these checklists will work for most of the single-engine twins, for most of the twin-engine aircraft that we fly today. Okay, we have an engine on fire. First thing we should do is pull the firewall shutoff valve or turn the fuel selector off, whichever your aircraft has. Then the mixture control, bring it back to the idle cutoff position. Then engine. Now you see what we've done here. By shutting off the fuel selector and the mixture, we have starved the fire of gasoline as a fuel. But as long as the engine is running, the oil pump might be some oil to the fire. So we want to feather the engine as soon as possible and get rid of the possibility of an oil fire. And now turn off the boost pump. As a matter of fact, if you can turn off the boost pump with your other hand while you're doing some of these checklist items, it would be even better. Now, simultaneously, again, maintain airspeed at or near the blue line and hold your heading within 10 degrees. These are the life-preserving actions, and they must be accomplished with precision and some degree of confidence. Now, raise the dead engine 4 or 5 degrees. Close the cowl flap on the dead engine. It's only creating an initial drag. And use the maximum continuous power and reduce the drag to the minimum. Maintain the VYSE speed, even though this may result in an altitude loss. And note that verification was not necessary. The fire and smoke is ample verification in this case. Now it almost goes without saying that win or lose, if the fire goes out or if it doesn't, you must never attempt a restart and you must land as quickly as you can safely do so. Well, Jack, I know you must feel as though you asked me for the time and I told you how to build a watch. But have I answered the questions that you initially posed?
Not only that, Tony, but you've brought up some new questions that I wouldn't have even thought of, and I certainly appreciate the time. You know, your business and my business are not that dissimilar. You teach avoidance, in other words, not getting into certain situations, and that's when I teach preventive medicine. When the situation is there, you're talking about doing the right thing the first time, and that's what I try to do.
Yes, you see, Jack, the mark of a safe pilot is not an ability to get out of trouble, but a capacity to avoid it in the first place. Now, when you first came in, you were a little bit uncertain as to whether you needed training or not. Have you made a decision?
I certainly have, Tony. I think about time for me to go out and get some advanced training, and the sooner the better. So, Doctor, why don't we go fly?